The neutron has no charge, zero, absolutely nothing, and yet it behaves like a magnet. That should be impossible. For nearly a century, physics students have been taught a simple rule: magnetism requires moving charge. A current, a spinning electron, something with an electric signature carving a field through space. The neutron has none of that. It is electrically neutral, down to the last decimal place we can measure. And still, when Otto Stern aimed a beam of neutrons through a magnetic field in the 1930s, they bent, they responded. They acted like tiny compasses spinning through the void, pulled by forces they had no right to feel. Stern won a Nobel Prize trying to explain it. He couldn't. For decades, the neutron sat at the center of nuclear physics like a fact that refused to make sense. It held the nucleus together, it powered stars, it built the periodic table, and no one could tell you why a particle with zero charge had a magnetic moment 2/3 as strong as a proton's. Then we looked inside, and what we found wasn't emptiness, it was a storm. A trio of quarks spinning at impossible speeds, their fractional charges cancelling perfectly to zero on the outside while generating magnetic chaos on the inside. The neutron wasn't neutral, it was balanced. And that balance, that perfect conspiracy of charge and spin, opened the door to some of the strangest mysteries in modern physics: the proton spin crisis. Magnetar fields strong enough to shred atoms from 1,000 miles away. The search for an electric dipole moment that could explain why the universe is made of matter at all. Every answer we've pulled from the neutron has led to 5 new questions, each one deeper and stranger than the last. This is the story of a particle that shouldn't exist the way it does, and what it's teaching us about the fabric of everything. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in. This is going to be a good one. There is a particle inside every atom in your body that has been lying to you your entire life. Not through omission, not through silence, through something more subtle, through the sheer fact of existing without making any sense whatsoever. It sits next to the proton in the nucleus of every element, heavier than hydrogen, holding the whole thing together, keeping atomic nuclei from flying apart under their own electrical repulsion. Without it, chemistry would not exist. Stars would not burn. You would not be here. And for the first 3 decades of the 20th century, nobody knew it was there. The neutron, electrically neutral, roughly the same size as a proton. Slightly heavier, though the difference is so small that it took careful measurement to even notice. When James Chadwick finally detected it in 1932, the discovery was less a revelation and more the resolution of a bookkeeping error that had been driving physicists quietly insane for years. Atomic nuclei had too much mass. The numbers did not add up. If you counted only the protons inside a nucleus, which were the only heavy particles anyone knew about at the time, the math came up short. A carbon atom, for instance, has 6 protons, 6 protons worth of positive charge, which matched the 6 electrons orbiting outside. That part was fine. But 6 protons worth of mass should have given carbon an atomic weight of 6. Instead, carbon weighed 12, double what it should have. For a while, the leading explanation was that nuclei contained extra protons paired with electrons to cancel out their charge. A carbon nucleus in this model would have 12 protons and 6 electrons. 12 units of mass, 6 units of net charge, problem solved. Except this explanation created more problems than it solved. Electrons are light, electrons are small, Electrons inside a nucleus that size would have to be moving at speeds close to the speed of light, and quantum mechanics, which was still being assembled piece by piece in the 1920s, said that confining an electron to such a tiny space would give it so much kinetic energy that it would immediately escape. The math did not allow it. The nucleus could not hold electrons. But if it did not hold electrons, where was the missing mass coming from? Chadwick's experiment was elegant in the way that only the best physics experiments are. He bombarded beryllium with alpha particles, high-energy helium nuclei, and noticed that the beryllium emitted some kind of radiation, not gamma rays, which had been the initial guess. This radiation could knock protons clean out of paraffin wax, which gamma rays were not energetic enough to do. Whatever this radiation was, it carried momentum and mass, and critically, it did not bend in a magnetic field. Charged particles curve when they pass through a magnetic field. Electrons curve one way, protons the other. This new radiation went straight through, no deflection, which meant no charge. Chadwick called it the neutron. The name was not new. Ernest Rutherford had speculated about the existence of a neutral particle years earlier, suggesting that a proton and an electron might somehow bind together into a single neutral object. But Rutherford's idea had been theoretical, a guess. Chadwick's neutron was real, detectable, and sitting inside every nucleus heavier than hydrogen. It solved the mass problem instantly. Carbon did not have 12 protons and 6 electrons. It had 6 protons and 6 neutrons. Oxygen had 8 protons and 8 neutrons. Uranium had 92 protons and over 100 neutrons, packed into a space smaller than the period at the end of this sentence. The periodic table finally made sense. The discovery earned Chadwick the Nobel Prize in 1935. And for a brief moment, the neutron seemed like the simplest particle in the universe, a proton without charge, a neutral lump of matter whose only job was to add mass and stabilize the nucleus. It did not interact with electrons. It did not respond to electric fields. It just sat there, inert and uncomplicated, doing exactly what you would expect a neutral particle to do, which is to say, nothing interesting. That lasted about 8 years. Here is the thing about neutral particles. Neutral, in physics, does not mean what it means in everyday language. When we say something is neutral in conversation, we usually mean it is inert, uninvolved. Switzerland during wartime, a bystander. But in particle physics, neutral can mean two very different things. It can mean the absence of charge, the way a photon has no charge because it is made of pure electromagnetic energy, or it can mean the cancellation of charge, the way a hydrogen atom has no net charge because the positive proton and the negative electron balance each other out. The first kind of neutrality is true emptiness. The second kind is a truce, a balance of opposing forces that could, under the right conditions, be pulled apart. For the first few years after its discovery, everyone assumed the neutron was the first kind of neutral, an absence, a blank space in the ledger where charge simply did not exist. That assumption made sense. The neutron did not respond to electric fields. It did not leave tracks in cloud chambers the way charged particles did. When neutrons passed through matter, they drifted through like ghosts, interacting only through the weak nuclear force and the occasional collision with an atomic nucleus. If you tried to study a neutron the way you studied a proton, using the standard tools of early 20th century physics, magnets and electric fields and deflection experiments, the neutron gave you nothing. It was invisible to almost every technique available, and because it was invisible, it was hard to study. Protons were easy. Fire a beam of protons through a magnetic field and they curve. Measure the curve, and you learn the proton's charge, its mass, its momentum, every property you care about. Electrons were even easier. Light, fast, responsive to the smallest electric nudge. But neutrons? Neutrons required a completely different toolkit. You could not see them directly. You could only infer their presence by watching what they did to other particles. You could watch a neutron smash into a nucleus and knock a proton loose. You could watch a neutron decay, splitting into a proton, an electron, and a neutrino after about 10 minutes of free existence. But you could not, in any straightforward way, just look at a neutron and measure its properties the way you could with a charged particle, which made the next discovery all the more shocking. In the late 1930s, physicists started doing something that should have been pointless. They started measuring the neutron's magnetic properties, not because they expected to find anything. Magnetic fields are generated by moving electric charges. That is not a theory. That is one of the foundational rules of electromagnetism, established by Hans Christian Ørsted in 1820, when he noticed that a compass needle deflected near a wire carrying electric current. Moving charge makes magnetism. No moving charge, no magnetism. The neutron had no charge, therefore the neutron should have no magnetism. End of story. Except the neutron did have magnetism. A lot of it. The first hints came from molecular beam experiments, a technique that had been used to measure the magnetic moments of atoms and nuclei with extraordinary precision. You take a beam of particles, pass it through an inhomogeneous magnetic field, one that is stronger in some regions than others, and watch how the beam deflects. Particles with magnetic moments, tiny internal magnets, will curve toward or away from the stronger part of the field, depending on their orientation. The amount of deflection tells you the strength of the magnetic moment. When experimentalists aimed this technique at particles containing neutrons, they started seeing deflections that did not match the predictions. At first, the assumption was that the magnetic signal was coming from the protons. Protons have magnetic moments. Protons are little magnets. That part was well understood. But as the measurements got more refined, it became clear that something else was contributing. The deflections were too large. The numbers did not add up unless the neutron itself had a magnetic moment. A particle with zero charge was behaving like a magnet. By 1940, the evidence was undeniable. The neutron had a measurable, reproducible, non-zero magnetic moment, and it was not small. The neutron's magnetic moment came in at about -1.913 nuclear magnetons. For comparison, the proton's magnetic moment is positive 2.79 nuclear magnetons. The neutron's moment is about 2/3 the size of the proton's, opposite in sign, and absolutely, categorically should not exist if the neutron is truly a neutral particle in the way everyone assumed neutral meant. That negative sign is worth pausing on. A magnetic moment has a direction. In a proton, the magnetic moment points in the same direction as the proton's spin. In a neutron, the magnetic moment points in the opposite direction. The neutron spins one way, and its internal magnet points the other way. That is not just unexpected, that is bizarre. It suggests that whatever is generating the neutron's magnetism is not behaving the way you would expect from a simple spinning sphere of matter. It suggests structure, internal complexity, parts moving in ways that do not align with the whole. This was the moment the neutron stopped being simple, the moment it became a problem. Because if the neutron is truly neutral, if it contains no net charge, then by every rule of classical electromagnetism, it should not have a magnetic field. Magnetic fields come from moving charges. If there are no charges moving inside the neutron, there is nothing to generate the field. And yet the field is there, measurable, reproducible, real. The only way out of the paradox is to admit that the neutron is not truly neutral in the way we thought. It is neutral by cancellation. It contains charges inside it. Positive charges and negative charges, moving, circulating, generating magnetic fields that do not cancel out even though the charges themselves sum to zero. The neutron is not an absence of charge, it is a balance of charges, a truce, and that truce, it turns out, has consequences. For years, physicists tried to work around this. They built models where the neutron was a bound state of a proton and an electron, held together by some unknown force. That model explained the mass, roughly. It explained the charge, sort of, but it could not explain the magnetic moment. The numbers did not work. No matter how you arranged a proton and an electron, you could not get the neutron's observed magnetic properties to fall out of the math. The neutron was not a proton plus an electron. It was something else, something that required a completely different way of thinking about what a particle is. The resolution, when it finally came, arrived not from experiments on neutrons, but from experiments on protons. In the 1950s and 60s, physicists began smashing protons together at higher and higher energies, and they started seeing debris. Lots of debris. Particles that had not been there before the collision. Particles that seemed to emerge from inside the proton itself. Pions, kaons, strange particles with properties that did not fit into any existing framework. The proton, it became clear, was not elementary. It was not a single indivisible point. It was a bag of smaller things, held together by forces no one fully understood yet. The neutron, by extension, had to be the same, a composite, a structure, and if it was a structure, then its magnetic moment made sense, not as a violation of the rules, but as a natural consequence of the internal dance of charges moving around inside a space too small to see. The neutron was neutral on the outside, but inside it was alive with motion. Charges spinning, circulating, generating magnetic fields that persisted even when the total charge added up to zero. That realization changed everything. It meant that the neutron was not a fundamental particle. It meant that protons and neutrons, the building blocks of the atomic nucleus, were themselves built from something smaller. And it meant that the next chapter of physics would have to dig deeper. Past the nucleus, past the nucleons, down into the structure of matter at a scale where the rules were not just different, but almost unrecognizable. The neutron, it turned out, was not a ghost, it was a door. And on the other side of that door was a universe of quarks, gluons, and forces that would take decades to map. The particle with no charge had magnetism, and that magnetism was the first clue that the universe had more layers than anyone had imagined. The problem with discovering something impossible is that you have to prove it twice, once to the universe and once to every physicist who thinks you made a mistake. Otto Stern spent most of the 1930s doing exactly that, and by the time he was finished, the neutron had gone from a simple neutral particle to a walking contradiction wrapped in a mystery that would take another 40 years to fully unpack. Stern was not new to impossible results. He had already built a career out of making atoms do things they were not supposed to do. Born in Germany in 1888, he spent his early years working in physical chemistry before drifting into the emerging field of quantum mechanics, where the rules were still being written and every experiment had the potential to rewrite them. By the early 1920s, he had teamed up with Walther Gerlach to perform what would become one of the most famous experiments in the history of physics. They called it the Stern-Gerlach experiment, and it was designed to answer a single straightforward question. When you put an atom in a magnetic field, Does its magnetic moment point in any direction it wants, or does it snap to specific allowed angles? Classical physics said the first option. An atom is a little magnet. Magnets can point anywhere. Tilt a bar magnet at any angle you like, and it stays there. There is no reason to think an atom should be different. Quantum mechanics, which was still more of a rumor than a theory, in 1921, suggested the second option. Angular momentum, the property tied to magnetic moments, might be quantized, restricted to discrete values. If that were true, an atom in a magnetic field would not smoothly align itself. It would snap to one of a few allowed orientations, like a dial that only clicks to certain positions. The experiment itself was elegant in the way that only the best physics experiments are. Stern and Gerlach heated a chunk of silver in a small oven until individual silver atoms began evaporating into a vapor. They let that vapor drift through a narrow slit to form a tight beam of atoms, all moving in roughly the same direction. Then they passed the beam through a region where a strong magnet had been carefully shaped to produce an inhomogeneous magnetic field. Not a uniform field where the strength is the same everywhere, but a field that was stronger at the top than at the bottom. A gradient. Here is why that matters. If an atom has a magnetic moment, a tiny internal magnet, it will feel a force when it moves through a magnetic field gradient. The strength and direction of that force depend on which way the atom's magnet is pointing. An atom whose magnetic moment points upward toward the stronger part of the field gets pulled upward. An atom whose moment points downward gets pulled downward. If the atoms can point in any direction, as classical physics predicted, the beam should spread out into a smooth, continuous blur on the detector screen at the end, a gradient of deflections corresponding to a gradient of orientations. That is not what happened. On February 7, 1922, Gerlach developed the detector plate and saw two distinct spots, two lines, separated by about 0.2 of a millimeter. Not a blur, not a spread. Two sharp, well-defined clusters of atoms. Half the atoms had deflected upward. Half had deflected downward, nothing in between. The magnetic moments of the silver atoms were not pointing in random directions. They were pointing in exactly two directions, up or down, quantized. The result was so unexpected that Gerlach sent Stern a postcard with a sketch of the split beam, and Stern, who was traveling at the time, reportedly showed it to everyone he met. This was not a subtle effect. This was nature drawing a line in the sand and saying the rules you think you understand do not apply here. The spatial orientation of angular momentum is quantized. Magnetic moments come in discrete states. The smooth, continuous world of classical mechanics stops at the atomic scale, and what replaces it is something stranger. The experiment made Stern famous. It also made him very good at measuring magnetic moments. Over the next decade, he refined the molecular beam technique into one of the most precise tools available in experimental physics. You could measure not just whether a particle had a magnetic moment, but exactly how strong that moment was. You could compare different particles. You could test predictions. You could, in theory, figure out what was going on inside the particle by studying how it responded to a magnetic field. In 1933, Stern turned that technique on the proton. The proton, everyone knew, had a positive charge. Charged particles moving in a circle generate magnetic fields. The proton also spins, or at least it behaves as if it does, which in quantum mechanics amounts to the same thing. A spinning charged sphere should produce a magnetic moment, and the size of that moment should be predictable based on the proton's charge, its mass, and its spin. The prediction was straightforward. One nuclear magneton, a unit of measurement tailored to the scale of atomic nuclei. Stern measured the proton and got 2.79 nuclear magnetons, not 1, 2.79, nearly 3 times larger than the theory said it should be. That result was uncomfortable. It suggested the proton was not a simple spinning ball of charge. It had internal structure. Something inside was moving in a way that amplified the magnetic moment beyond what a uniform sphere could produce. But in 1933, nobody knew what that something was. The Quark model was still 30 years away. Stern's result was filed under interesting, awarded a Nobel Prize in 1943, and left as a puzzle for future theorists to solve. Then came the neutron. Chadwick discovered it in 1932. By 1934, physicists had confirmed its mass, its neutrality, and its role in the nucleus. And because the neutron was neutral, because it had zero electric charge, everyone assumed it would have zero magnetic moment. No charge means no moving charge. No moving charge means no magnetism. The logic was airtight. Except molecular beam experiments on the deuteron, the nucleus of heavy hydrogen, started giving strange results. The deuteron is simple: one proton, one neutron, bound together. If you measure the deuteron's magnetic moment and subtract the proton's contribution, what is left over should tell you about the neutron. When physicists did that subtraction, they did not get zero, they got a number. A magnetic moment pointing in the opposite direction from the proton's moment, with a magnitude of about 1.91 nuclear magnetons. The neutron had a magnetic moment, a strong one, roughly 2/3 the size of the protons, but pointed the other way. A particle with no net charge was behaving like a magnet. To understand why that is a problem, you need to understand what a magnetic moment actually is. In classical physics, a magnetic moment comes from a loop of electric current. Take a wire, bend it into a circle, run a current through it, and the loop generates a magnetic field. The strength of that field depends on how much current is flowing and how big the loop is. The direction of the field depends on which way the current is moving. That is it. That is the entire recipe. Current in a loop makes a magnet. Now scale that down to a particle. A proton is not a loop of wire, but it has charge and it spins. If you treat the proton's charge as smeared out over the surface of a spinning sphere, the spinning motion is mathematically equivalent to a current loop. Charge moving in a circle, that generates a magnetic field. The size of the field depends on how much charge you have, how fast it is spinning, and how that charge is distributed. The proton's magnetic moment is larger than expected, which suggests the charge is not evenly distributed, but at least the mechanism makes sense. There is charge. It is moving. You get a magnet. The neutron has no charge, zero. If you try to apply the same reasoning, you immediately run into a wall. You cannot have a current loop without current. You cannot have current without charge. The neutron should be magnetically inert, and yet it is not. The only way out of this is to admit that the neutron is not truly neutral in the way we thought. It is neutral by cancellation. Somewhere inside the neutron, there are positive charges and negative charges, distributed in such a way that they sum to zero when you add them all up, but not distributed uniformly. The positive charges are concentrated in some regions, the negative charges are concentrated in others, and when the neutron spins, those separated charges move in loops, generating magnetic fields that do not cancel out even though the total charge is zero. Think of it this way. Imagine a spinning disk with a positive charge on the outer edge and a negative charge in the center. The total charge is zero. Positive and negative balance. But the positive charge is moving in a larger loop than the negative charge because it is farther from the center. Larger loop, stronger magnetic field. The two fields do not cancel. You end up with a net magnetic moment even though the net charge is zero. That is what the neutron is doing, somehow. Stern did not have the tools to see inside the neutron. Nobody did. But he could measure the magnetic moment, and the magnetic moment was a clue. It was a fingerprint, a signature of internal structure that should not be there if the neutron were truly elementary. The neutron was hiding something, and whatever it was hiding, it was moving. The magnetic moment also had a direction problem. The proton's magnetic moment points in the same direction as its spin. Spin up, magnetic moment up. That is what you expect from a spinning charged object. The neutron's magnetic moment points in the opposite direction. Spin up, magnetic moment down. That is not what you expect from any simple model. It suggests that whatever is generating the neutron's magnetic field is not aligned with the overall spin of the particle. The pieces inside are doing their own thing, and the net result is a magnetic moment that points backward. By the late 1930s, the evidence was undeniable. The neutron had a measurable, reproducible, non-zero magnetic moment of about -1.913 nuclear magnetons. That negative sign is the direction, opposite the spin. The magnitude is about 2/3 of the proton's moment. Not a small effect, not a rounding error, a real, significant magnetic field coming from a particle that should not be able to produce one. Physicists tried to build models. One idea was that the neutron was a bound state of a proton and an electron glued together by some unknown force. That would give you neutral charge. It would give you roughly the right mass. And it would give you moving charges inside, which could generate a magnetic moment. But when you ran the numbers, the magnetic moment came out wrong. The model predicted a moment much smaller than what Stern measured, and there were other problems. Electrons confined to a space the size of a neutron would have enormous kinetic energy, enough to escape immediately. The nucleus could not hold them. The model did not work. Another idea was that the neutron was surrounded by a cloud of virtual particles, fleeting quantum fluctuations that popped in and out of existence too quickly to be detected directly, but still contributed to the neutron's properties. In quantum field theory, which was still being developed in the 1940s, particles are not isolated points. They are surrounded by a haze of virtual particles constantly being created and annihilated. If some of those virtual particles were charged, they could generate a magnetic field even if the central particle itself had no charge. That idea was closer to the truth, but in the 1940s it was too vague to be useful. Nobody knew what the virtual particles were or how to calculate their contribution. The real answer, when it finally came, required a completely different way of thinking about what particles are. The neutron is not made of a proton and an electron. It is not a point surrounded by a cloud. It is a composite object made of smaller pieces called quarks, held together by particles called gluons, and the whole system is so dynamic, so constantly shifting and fluctuating, that the idea of the neutron having fixed internal parts is almost misleading. The neutron is more like a storm than a stone. A pattern of energy and matter that holds its shape, not because the pieces are locked in place, but because the forces between them are balanced. Inside the neutron, there are 3 quarks, 2 down quarks, each with a charge of -1/3, and 1 up quark with a charge of +2/3. Add them up, -1/3, -1/3, +2/3, total charge 0. But those quarks are not sitting still. They are moving, they are spinning. They are interacting with the gluons that bind them together, and those gluons are themselves carrying energy and momentum and contributing to the overall properties of the neutron. The distribution of charge inside the neutron is not uniform. The up quark, with its positive charge, spends more time in certain regions. The down quarks, with their negative charges, spend more time in others, and when the whole system spins, the moving charges generate magnetic fields. The down quarks dominate numerically, 2 of them to 1 up quark. And because they carry negative charge, the net magnetic moment of the neutron comes out negative, opposite the spin. The up quark contributes a positive moment, but it is outnumbered. The result is a magnetic moment of about negative 1.913 nuclear magnetons, almost exactly 2/3 the size of the proton's positive 2.79 nuclear magnetons. The ratio is not a coincidence. It comes directly from the quark content of the 2 particles. The proton has 2 up quarks and 1 down quark. The neutron has 2 down quarks and 1 up quark. Flip the ratio, flip the magnetic moment. But Stern did not know any of that. In the 1930s, the idea that protons and neutrons were made of smaller particles was not even on the table. The tools to probe that deep did not exist yet. What Stern had was a measurement, a number, a magnetic moment that should not be there, coming from a particle that should not have one. And that number was the crack in the foundation, the place where classical physics stopped working and something new had to begin. The importance of Stern's result cannot be overstated. It was not just a curiosity, it was a direct, unambiguous signal that the neutron had internal structure, that the particles we thought were fundamental were not, that the building blocks of the nucleus were themselves built from something smaller. The neutron's magnetic moment was the first solid evidence that we needed to dig deeper, that there was another layer beneath the layer we had just uncovered. Stern himself never saw the full picture. He left Germany in 1933, the same year he measured the proton's magnetic moment, fleeing the rise of the Nazi regime. He spent the rest of his career in the United States, continuing his work on molecular beams and magnetic moments. But the theoretical framework to interpret his neutron results did not arrive until the 1960s. By then, Stern had retired. He died in 1969, the same year that deep inelastic scattering experiments at Stanford confirmed the existence of point-like particles inside the proton, the particles that would come to be called quarks. The neutron's magnetic moment sat there like a crack in the foundation of a house everyone thought was solid. You could ignore it for a while. You could walk around it. You could tell yourself it was probably nothing. But every time a physicist ran the numbers, every time someone tried to build a model that explained what was happening inside that neutral particle, the crack got wider. By the 1950s, it was clear that ignoring the problem was no longer an option. The neutron was not what it appeared to be. And if the neutron was hiding something, then everything physicists thought they understood about the structure of matter was probably wrong too. The crisis was not limited to the neutron. By the early 1960s, particle physics had become a zoo, literally. Physicists started calling it the particle zoo, and the name was not affectionate. Every time someone built a bigger particle accelerator and smashed protons together at higher energies, new particles came spilling out of the wreckage. Pions, kaons, lambda particles, sigma particles, Xi particles, delta particles, strange particles with strange properties. Particles that lived for a fraction of a second before decaying into other particles. Particles that seemed to come in families with similar masses and charges but slightly different behaviors. By 1961, the Particle Data Group's list of known particles had grown to over 100 entries, 100 supposedly fundamental particles. That was not a theory, that was a phone book. The word fundamental was starting to lose all meaning. In chemistry, when Dmitri Mendeleev organized the elements into the periodic table in 1869, he found patterns, elements with similar properties lined up in columns. Atomic masses increased in predictable steps. The table had structure, and that structure suggested an underlying order. By the early 20th century, physicists understood why. Elements were not fundamental. They were made of smaller pieces, protons, neutrons, and electrons arranged in different combinations. Once you knew the rules, the periodic table made perfect sense. Particle physics in the 1950s looked like the periodic table before Mendeleev. A list of names with no organizing principle. No one knew why some particles were heavier than others. No one knew why some decayed quickly and others lived longer. No one knew why certain combinations showed up in experiments while others never did. The proton and the neutron, the two particles everyone thought they understood, were surrounded by a crowd of cousins, siblings, and distant relatives that behaved in ways no existing theory could predict. The field was drowning in data with no map to guide it. Then two physicists, working independently on opposite sides of the planet, proposed the same radical idea. The particles were not fundamental, they were composite, made of smaller pieces. And if you assumed the right pieces with the right properties, all the patterns in the particle zoo suddenly clicked into place. Murray Gell-Mann was a theoretical physicist at Caltech, with a reputation for brilliance and an ego to match. He had already made a name for himself by introducing the concept of strangeness, a new quantum number that helped explain why certain particles decayed more slowly than expected. By 1961, he had started organizing hadrons, the family of particles that included protons, neutrons, pions, and all the strange newcomers, into patterns based on their charge, mass, and other properties. He called the scheme the Eightfold Way, a reference to Buddhism that annoyed some of his colleagues and delighted others. The Eightfold Way worked. It predicted the existence of particles that had not been discovered yet, and when experimentalists went looking, they found them. But Gell-Mann did not stop at patterns. Patterns are descriptions. They tell you what is happening, but not why. In 1964, Gell-Mann took the next step. He proposed that hadrons were made of smaller particles he called quarks. The name came from a line in James Joyce's Finnegan's Wake, 3 quarks for muster mark. Gell-Mann liked the sound of it, and the number 3 turned out to be important. Most hadrons, he suggested, were built from 3 quarks bound together in specific combinations. The proton, the neutron, the lambda, the sigma, all of them were triplets of quarks. Different combinations gave you different particles. Change the quarks, change the properties. At almost exactly the same time, George Zweig, a physicist working at CERN in Switzerland, proposed the same idea. Zweig called his particles aces, not quarks, and his paper was slightly more detailed in some areas, but the core idea was identical. Hadrons are composite. The hundreds of particles in the zoo are not fundamental. They are built from a small number of fundamental pieces arranged in different ways. Zweig's paper was less widely circulated, partly because CERN's bureaucracy delayed its publication, and partly because Gell-Mann was better at self-promotion. History remembers the idea as the Quark model, not the ace model, but both men deserve credit for seeing the same truth at the same moment. The Quark model started with 3 types of quarks. Gell-Mann called them up, down, and strange. Each quark had a spin of 1/2, the same as an electron or a proton. But unlike any particle anyone had ever seen, quarks had fractional electric charge. The up quark had a charge of positive 2/3. The down quark had a charge of negative 1/3. The strange quark also had a charge of negative 1/3, but it was heavier and contributed the property Gell-Mann had named strangeness a few years earlier. Fractional charge was the part that made people uncomfortable. Every particle ever detected in a laboratory had a charge of 0, plus or minus 1, plus or minus 2, always an integer multiple of the electron's charge. Quarks broke that rule. An up quark had a charge of positive 2/3 of an electron charge. A down quark had negative 1/3. No one had ever seen anything like it. The numbers were strange enough that even Gell-Mann, in his original paper, hedged his language. He presented quarks as a mathematical convenience, a useful fiction for organizing the patterns, not necessarily real objects you could pull out of a proton and hold in your hand. But the model worked too well to be fiction. Take 3 quarks, combine them according to the rules, and you could build every hadron on the list. A proton, for instance, was made of 2 up quarks and 1 down quark. Add up the charges, 2/3 plus 2/3 minus 1/3. You get +1, the charge of the proton. A neutron was 2 down quarks and 1 up quark. Negative 1/3 minus 1/3 plus 2/3. You get 0, the charge of the neutron. Change the combination and you get different particles. 3 up quarks give you a delta ++, a short-lived particle with a charge of +2. 3 down quarks give you a delta minus, charge -1. The math worked. Every time. The quark model also explained the neutron's magnetic moment, the paradox that had been sitting unsolved since the 1930s. Magnetic moments come from spin and charge. Quarks have both. An up quark, with its positive 2/3 charge and its spin, generates a small magnetic moment. A down quark, with its negative 1/3 charge and its spin, generates a smaller magnetic moment in the opposite direction. Put 2 down quarks and 1 up quark together, and the individual moments do not cancel. They add up in a complicated way that depends on how the quarks are arranged and how they are moving inside the neutron. The net result is a magnetic moment of about -1.913 nuclear magnetons, opposite the neutron's spin, exactly what Stern measured. The numbers were not a coincidence. The quark model predicted the magnetic moments of the proton and the neutron based purely on the charges and spins of the quarks inside. When physicists ran the calculation, the predicted value for the neutron came out within a few % of the measured value. That was not something you could wave away. That was evidence, not proof, not yet, but a strong hint that quarks were more than just a bookkeeping trick. They were real objects with real properties, and those properties added up to explain one of the biggest mysteries in nuclear physics. Here is the key insight. The neutron is neutral because the charges of its quarks sum to 0. But the magnetic moments do not sum to 0 because the quarks are not identical and they are not arranged symmetrically. The 2 down quarks dominate the magnetic behavior because there are 2 of them, and because the negative charge, even though it is smaller in magnitude, contributes more strongly when you account for how the quarks are distributed inside the neutron. The up quark pulls in one direction. The 2 down quarks pull in the other direction. The down quarks win. The result is a net magnetic moment that points opposite the neutron's spin. Think of it this way. Imagine you have a merry-go-round spinning in place. On the outer edge, you place 2 children running clockwise. Closer to the center, you place 1 child running counterclockwise. The merry-go-round itself is not moving forward or backward. Its center of mass stays in one place, neutral. But the children are generating motion. The two on the outside are covering more ground because they are farther from the center. The one near the center is moving slower. If you tried to measure the total rotational momentum of the system, you would not get zero. You would get a net value determined by the imbalance between the outer runners and the inner runner. The neutron works the same way. The quarks are the runners. Their charges and spins are the motion. The neutron as a whole is neutral, but the internal motion is not balanced. The quark model also explained why you could never pull a single quark out of a proton or neutron and study it in isolation. The force holding quarks together, which would later be named the strong force or the color force, gets stronger as you try to separate them. It is the opposite of gravity or electromagnetism, which weaken with distance. Pull two quarks apart and the force between them increases. Keep pulling, and eventually you pump so much energy into the system that the energy itself converts into new quarks. Instead of isolating one quark, you create a pair of quarks. The original particle splits into two new particles, each containing quarks, and you are back where you started. Quarks are confined permanently. You can never see one by itself. You can only see them in combinations. That confinement explained why no one had detected fractional charges in any experiment. If quarks are always bound together in groups of 2 or 3, and if the groups always add up to integer charges, then every particle you ever detect in a detector will have an integer charge. 0, +1, -1, +2, never 2/3, never 1/3. The fractional charges are hidden inside. You can infer they are there from the magnetic moments, from the patterns in the particle zoo, from the way particles decay and interact. But you cannot see them directly. The universe does not let you. By the mid-1960s, the quark model had gained enough traction that experimentalists started designing tests. If quarks were real, they should leave fingerprints in high-energy collisions. When you smash an electron into a proton at extremely high energy, the electron should scatter off the individual quarks inside the proton, rather than bouncing off the proton as a whole. The scattering pattern should show evidence of point-like constituents inside the proton, hard little lumps that deflect the electron at large angles. The experiments were done at the Stanford Linear Accelerator Center, starting in 1967. Physicists fired a beam of high-energy electrons at a target filled with liquid hydrogen, which is just protons surrounded by electrons. They measured how the electrons scattered. If the proton were a smooth blob of charge spread out evenly, the scattering would follow a predictable pattern, with most electrons deflecting at small angles. If the proton contained point-like particles inside, some electrons would hit those particles head-on and scatter backward at large angles. The latter is what they saw. Deep, inelastic scattering, they called it, and the results were unambiguous. The proton was not smooth, it was lumpy. It contained hard point-like objects that experimentalists started calling partons before everyone agreed they were the same thing as Gell-Mann's quarks. The Nobel Prize for that discovery went to Jerome Friedman, Henry Kendall, and Richard Taylor in 1990. By then, the quark model had been confirmed by so many independent experiments that no serious physicist doubted it anymore. The proton and the neutron, the particles everyone had thought were fundamental, were composites. They were made of quarks. And those quarks, with their fractional charges and their intrinsic spins, were the real building blocks of matter. 3 types of quarks were enough to build the proton, the neutron, and most of the particles in the original zoo. But as experiments got more sophisticated, physicists discovered that 3 was not enough. There were more quarks. In 1974, experimentalists discovered a new particle called the J-psi, which contained a 4th type of quark called charm. In 1977, they found evidence of a fifth quark called bottom, or sometimes beauty. And in 1995, after years of searching, they finally detected the sixth quark called top. 6 quarks in total, 3 pairs, up and down, charm and strange, top and bottom. Each pair consists of 1 quark with charge positive 2/3 and 1 with charge negative 1/3. The pattern holds. The lightest quarks, up and down, make up the protons and neutrons in every atom in your body. The heavier quarks, charm, strange, top and bottom, only appear in high-energy collisions or inside exotic particles that decay almost immediately. In a sense, ordinary matter is built from just 2 types of quarks, up and down. Everything else is rare, short-lived, and irrelevant to the everyday structure of the universe. But the existence of 6 quarks instead of 3 raised new questions. Why 6? Why 3 pairs? Why this specific pattern of masses and charges? The Quark model answered the question of what protons and neutrons are made of, but it opened the door to a deeper question. What determines the properties of the quarks themselves? Why does the up quark have a charge of positive 2/3 and a mass of about 2 megaelectron-volts, while the top quark has the same charge but a mass of about 173 gigaelectron-volts, roughly 80,000 times heavier? The Quark model solved one mystery and replaced it with another. The neutron's magnetic moment, the paradox that started all of this, was no longer a paradox. It was a prediction, a consequence of the quark structure Gell-Mann and Zweig had proposed. The neutron is neutral because its quarks have charges that sum to 0. But it has a magnetic moment because those quarks have spin, and spin plus charge equals magnetism. The 2 down quarks, each with their negative 1/3 charge, generate magnetic moments that together outweigh the contribution of the single up quark. The result is a net magnetic moment pointing opposite the neutron's spin, with a magnitude of about negative 1.913 nuclear magnetons. The number matches the measurement. The model works. The story of the Quark model is often told as a triumph of theory. Gell-Mann and Zweig saw patterns in the data, proposed an explanation, and experiments confirmed they were right. That is true, but it leaves out the messiness. For years after the original proposal, many physicists treated quarks as mathematical constructs, useful fictions that organized the data but did not necessarily correspond to real objects. Gell-Mann himself was cautious in his language, leaving open the possibility that quarks were just a convenient way to describe hadron symmetries without being actual particles you could detect. It was only after the deep inelastic scattering experiments at Stanford that the reality of quarks became unavoidable. The proton contained point-like constituents. Those constituents had fractional charge. They were quarks. The fractional charge, strange as it seemed, was the key. If quarks had integer charges, they would just be smaller versions of protons and electrons, and nothing about particle physics would make sense. The fractional charges, combined with the rule that quarks are always confined in groups, explained why every particle ever detected has an integer charge. The fractions are always hidden inside. You see their effects in magnetic moments, in scattering experiments, in decay patterns, but you never see a lone quark drifting through space with a charge of 2/3. Nature does not allow it. The Quark model also explained why the periodic table of elements stops where it does. Protons and neutrons are stable, or at least long-lived. The free neutron decays after about 10 minutes, but inside a nucleus, neutrons can last billions of years. That stability comes from the quarks inside. Quarks are bound so tightly by the strong force that under normal conditions they do not fall apart. Build a nucleus out of protons and neutrons, and the nucleus inherits that stability. Build atoms, molecules, planets, and people, and everything rests on the fact that quarks stay put. If quarks were unstable, if they decayed quickly into lighter particles, matter as we know it would not exist. The universe would be a thin soup of radiation with no structure, no chemistry, no life. The neutron, the particle that started this whole line of inquiry, was no longer a ghost. It was a bag of quarks. 2 down quarks and 1 up quark, held together by gluons, the particles that carry the strong force. The gluons themselves are another story, a deeper layer of complexity that would take another decade to fully map. But by the early 1970s, the basic picture was clear. Protons and neutrons are not fundamental. They are made of quarks. Quarks have fractional charges and intrinsic spins. Those spins generate magnetic moments, and the magnetic moments, when combined according to the rules of quantum mechanics, explain why the neutron has a magnetic field even though its total charge is 0. The universe within had been unveiled. The neutron was not a single object. It was a dynamic, churning system of quarks and gluons, bound together by forces so strong that you could never pull them apart. And those quarks, moving and spinning inside a space smaller than an atom's nucleus, were generating effects that Stern measured in the 1930s without having any idea what was causing them. The neutron had a secret, and the secret was quarks. The next question was how those quarks stayed bound together, and that question would require an entirely new theory, a theory of the strong force, a theory of color, a theory that would make the quark model look simple by comparison. Here is where the story gets strange in a different way, because discovering that protons and neutrons are made of quarks did not solve the problem. It moved the problem. If quarks are real, if they are sitting inside every proton and every neutron in your body right now, then something has to be holding them together, and whatever that something is, it has to be powerful, extraordinarily powerful. Because quarks do not want to stay together. They are electrically charged. Some of them have the same type of charge. Put 2 particles with the same electric charge next to each other, and they repel. Push them closer, and the repulsion gets stronger. The electromagnetic force should tear the inside of a proton apart. It does not. Something else is holding the quarks in place. Something strong enough to overpower electromagnetism at distances smaller than the width of an atomic nucleus. Physicists needed a new force, a force no one had ever directly measured, because it only operates at ranges so small that until the 1960s, no experiment could probe that deep. They called it the strong force, and the theory that describes it is called quantum chromodynamics, QCD for short. And the moment you start digging into QCD, every intuition you have about how forces work stops being useful. The name itself is a clue. Chromodynamics. Chromo comes from the Greek word for color, not the kind of color you see with your eyes, a different kind of color, a property that quarks carry the same way electrons carry electric charge. Except instead of one type of charge, positive or negative, quarks carry one of 3 types of color charge. Physicists call them red, green, and blue because they needed labels, and those labels worked as well as any other. The names are arbitrary. Quarks are not actually colored. They do not emit light. They do not have hues. The color charge is an internal quantum property that determines how quarks interact with the force that binds them. Pick different names if you want. Call them Alice, Bob, and Charlie. Call them 1, 2, and 3. The labels do not matter. The behavior does. Here is the rule. Quarks must combine in such a way that their total color charge is neutral. In practice, this means one of 2 things. Either you combine 3 quarks, one red, one green, one blue, and the 3 colors cancel out to white, which is color neutral. Or you combine a quark and an antiquark, where the antiquark carries the opposite color charge, and the two cancel directly, red and anti-red, green and anti-green, blue and anti-blue. Both combinations give you a color-neutral object, and only color-neutral objects are allowed to exist as standalone particles in the universe. Everything else is confined. The proton is 3 quarks, 2 up quarks and 1 down quark. One of those quarks is red, one is green, one is blue. Add them up and you get white, color neutral. The neutron is also 3 quarks, 2 down and 1 up, same rule. 1 red, 1 green, 1 blue, neutral. A pion, one of the lighter particles in the particle zoo, is a quark and an antiquark. Red and anti-red, for instance, also neutral. The combinations vary, but the rule never changes. If you want to exist as a free particle, you have to be color neutral. This is why you can never pull a single quark out of a proton and study it in isolation. A single quark is not color neutral. It carries red charge, or green charge, or blue charge. The universe does not allow particles with unbalanced color charge to roam free. If you try to pull a red quark out of a proton, the force holding it in place does not weaken as you pull, it gets stronger. Keep pulling, and you are fighting against a force that increases with distance, which is the exact opposite of every other force you have ever experienced. Pull hard enough, and eventually you pump so much energy into the system that the energy itself converts into a quark-antiquark pair. The original quark pairs up with the new antiquark to form a color-neutral particle. The leftover quark joins the remaining quarks in the proton to form another color-neutral particle. You started with 1 proton, you ended with 2 particles, both color-neutral. You never got your isolated quark. You never will. This behavior is called confinement, and it is one of the defining features of quantum chromodynamics. Quarks are permanently confined inside color-neutral particles. You can infer their existence. You can measure their properties indirectly. You can watch them interact inside protons and neutrons by scattering electrons off them at high energies. But you cannot extract one and put it on a shelf. The strong force will not let you. The particles that carry the strong force are called gluons, and they were introduced into the theory in 1972 by Harold Fritz and Murray Gell-Mann. The name is straightforward. Gluons glue quarks together. They are the messengers of the strong force, the same way photons are the messengers of the electromagnetic force. When 2 quarks interact, they exchange gluons. The gluons carry color charge from one quark to the other, changing the color of the quarks in the process. A red quark emits a gluon carrying red and anti-green color charge. The quark itself turns green. Another quark absorbs the gluon and turns red. The exchange happens constantly, billions upon billions of times per second inside every proton and neutron in existence. The colors are not fixed. They are flickering, shifting, swapping in a constant high-energy dance that never stops. Here is where gluons get weird. Photons do not carry electric charge. When a photon travels from one charged particle to another, it does not interact with itself. It is a passive messenger. Gluons are not passive. Gluons carry color charge, and because they carry color charge, they interact with each other. A gluon emitted by one quark can absorb or emit other gluons on its way to a second quark. Gluons interact with gluons. The force carriers interact with themselves. That self-interaction makes the strong force behave in ways that have no analogy in electromagnetism. It makes the force highly nonlinear, and it makes the math that describes the force extraordinarily difficult to solve. Quantum chromodynamics is a type of theory called a non-abelian gauge theory. The mathematical structure is built around a symmetry group called SU3, which describes how the three color charges transform into each other under the rules of the strong force. If you do not have a background in group theory or quantum field theory, those words probably sound like nonsense. That is fine. The key point is that QCD is not a simple extension of electromagnetism. It is a fundamentally different kind of theory with fundamentally different behavior, and that difference shows up in almost every prediction the theory makes. The strong force is extraordinarily powerful at the distances where it operates. Inside a proton, the force binding quarks together is roughly 100 times stronger than the electromagnetic force trying to push them apart. That is why protons do not explode. The strong force wins. But here is the twist. The strength of the strong force depends on the distance between the quarks. At very short distances, smaller than the size of a proton, the force gets weaker. At slightly larger distances, comparable to the size of a proton, the force is at its strongest. Pull the quarks farther apart, and the force does not drop off the way gravity or electromagnetism would. It stays strong. In fact, it increases. The force behaves like a spring. Stretch it, and it pulls back harder. This property is called asymptotic freedom, and it was discovered in 1973 by David Gross and Frank Wilczek, and independently by David Politzer. The discovery was so important that all three physicists won the Nobel Prize in Physics in 2004. Asymptotic freedom means that at very high energies, when quarks are slammed together hard enough that they get extremely close to each other, they behave almost as if they are free particles. The strong force weakens at short distances, so the quarks can move around almost independently for a brief moment. Then, as they start to separate, the force kicks in. The gluons tighten their grip. The quarks are pulled back together, and confinement takes over. This is why deep inelastic scattering experiments at Stanford in the late 1960s saw evidence of point-like particles inside the proton. The electrons were hitting the quarks at such high energy that for a fraction of a second the quarks acted like free particles. But that freedom was temporary. The moment the interaction ended, the quarks were confined again. The inside of a neutron, or a proton, is not a calm place. It is not three quarks sitting still in fixed positions like marbles in a bag. It is a chaotic, high-energy environment where quarks and gluons are constantly being created and destroyed. The three quarks that give the neutron its identity, 2 down quarks and 1 up quark, are called valence quarks. They are the quarks that determine the neutron's overall properties, its charge, its spin, its flavor. But they are not the only quarks inside. At any given moment, the neutron contains a seething sea of virtual quarks and antiquarks, popping into existence for fractions of a second before annihilating each other and disappearing. Those virtual quarks are created by the energy of the gluons binding the valence quarks together. The gluons are so energetic that they spontaneously create quark-antiquark pairs out of the vacuum, and those pairs contribute to the neutron's properties even though they do not stick around for long. The US Department of Energy has described this environment as a soup. Quarks and gluons in this soup constantly interact. The word soup is not a metaphor. It is an accurate description of what quantum chromodynamics predicts. The neutron is not a solid object. It is a dynamic, fluctuating system, a bound state of quantum fields that happens to hold its shape long enough to behave like a particle. And the shape it holds is determined by the constant exchange of gluons between the quarks, the self-interactions of those gluons with each other, and the endless creation and annihilation of virtual quark-antiquark pairs in the background. That dynamic environment is what gives the neutron its magnetic moment. The valence quarks are moving, the virtual quarks are moving, the gluons are moving. All of them carry energy and momentum, and many of them carry electric charge. When the whole system spins, the moving charges generate magnetic fields. The two down quarks, with their negative one-third charges, dominate the magnetic contribution because there are two of them and because they spend more time in the outer regions of the neutron, where their motion has a larger effect. The up quark, with its positive two-thirds charge, contributes a magnetic moment in the opposite direction, but it is outnumbered and outweighed. The result is a net magnetic moment of about negative 1.913 nuclear magnetons, pointing opposite the neutron's spin. The Quark model predicted this. QCD explains why. The strong force does not just hold quarks together inside protons and neutrons. It also holds protons and neutrons together inside atomic nuclei. This is called the residual strong force, and it is a kind of spillover effect. The gluons binding quarks inside a proton do not stop exactly at the proton's edge. They extend slightly beyond it, and when two protons or two neutrons or a proton and a neutron get close enough, their gluon fields overlap. The overlap creates an attractive force between the particles, strong enough to overcome the electromagnetic repulsion between protons. Without the residual strong force, atomic nuclei would not exist. Protons would repel each other. Atoms heavier than hydrogen would never form. Chemistry would be impossible. The fact that you are made of atoms containing carbon, oxygen, nitrogen, and dozens of other elements is a direct consequence of quantum chromodynamics. The strong force built the periodic table. QCD was identified as the correct field theory of the strong interaction in the early 1970s, and the term quantum chromodynamics was introduced by Fritz and Gell-Mann in 1972. By the end of the decade, the theory had been tested against experiment after experiment, and every test came back consistent. The theory predicted the existence of gluons. Gluons were detected. The theory predicted asymptotic freedom. Experiments confirmed it. The theory predicted confinement. No one has ever seen a free quark. The theory predicted the masses of certain hadrons, the decay rates of others, the behavior of quarks and gluons in high-energy collisions. The predictions matched the data. There is one piece of QCD that remains unproven in a strict mathematical sense, and that is confinement itself. Confinement is overwhelmingly supported by experimental evidence and by numerical simulations on supercomputers using a technique called lattice QCD. Lattice QCD treats space and time as a grid of discrete points and calculates the behavior of quarks and gluons on that grid using brute force computation. The results agree with experiments. They show confinement. They show that quarks cannot escape. But no one has yet produced a rigorous analytical proof, starting from the equations of QCD and deriving confinement as a mathematical theorem. The Clay Mathematics Institute has offered a $1 million prize for a solution to this problem. It is one of the 7 Millennium Prize problems, and it remains unsolved. That does not mean confinement is in doubt. It means the mathematical structure of QCD is so complex that proving things rigorously is extraordinarily hard. The theory works. The predictions match reality. Confinement is real. We just do not have a formal proof written in the language of pure mathematics. That gap bothers some physicists and does not bother others. The universe does not care whether we have a proof. It confines quarks regardless. The dynamic sea of quarks and gluons inside the neutron has another consequence. It means that most of the neutron's mass does not come from the quarks themselves. The up quark has a mass of about 2 megaelectronvolts. The down quark has a mass of about 5 megaelectronvolts. Add up the masses of 2 down quarks and 1 up quark, and you get roughly 12 megaelectronvolts. The neutron's mass is 940 megaelectronvolts. The quarks account for a little over 1% of the total. The rest comes from the energy of the gluons and the kinetic energy of the quarks as they move around inside the neutron. Einstein's equation, energy equals mass times the speed of light squared, works in reverse. Mass equals energy divided by the speed of light squared. The neutron is mostly energy, bound energy. Energy locked inside the strong force field that holds the quarks together. You are mostly energy. The protons and neutrons in your body, which make up nearly all of your mass, are almost entirely composed of the energy stored in the gluon field inside them. Less than 2% of your mass comes from the actual matter of the quarks. The rest is force. That realization is one of the strangest and most profound consequences of quantum chromodynamics. Matter, at its core, is not stuff. It is frozen energy, structure held in place by forces. The neutron is not a thing, it is a process, a stable pattern of interacting fields that happens to last long enough to be called a particle. And the fact that this process generates a magnetic field, even though the process as a whole has no net electric charge, is just one more piece of evidence that the universe at small scales is nothing like the universe you experience in your everyday life. QCD also explains why the strong force has such a short range. Gluons, unlike photons, are not observed as free particles. They are confined just like quarks. When gluons are exchanged between quarks inside a proton or neutron, they do not travel far. The range of the strong force is limited to distances on the order of 1 femtometer, which is 1 quadrillionth of a meter, roughly the size of a proton. Beyond that distance, the force drops to nearly zero. This is why the strong force does not affect your daily life. It operates entirely within the nucleus. You never feel it. You never see its effects directly. But without it, you would not exist. The theory of quantum chromodynamics sits at the foundation of the Standard Model of particle physics. The Standard Model is the best description we have of how the universe works at the smallest scales. It describes 3 of the 4 fundamental forces: electromagnetism, the weak force, and the strong force. Gravity is not included, which is a problem for another day. The strong force, governed by QCD, is responsible for the existence of protons and neutrons, and therefore for the existence of atomic nuclei, and therefore for the existence of atoms, molecules, planets, and everything made of them. If QCD were different, if the strong force were slightly weaker or slightly stronger, the universe would look completely different. Make the force too weak, and atomic nuclei fall apart. Make it too strong, and protons stick together so tightly that hydrogen fuses into helium in the early universe before stars ever form. The parameters of QCD sit in a narrow range that allows for complex chemistry and stable matter. We live in that range. We do not know why. The neutron, with its magnetic moment and its internal structure of quarks and gluons, is a window into the strong force. Every time you measure the neutron's properties, you are probing the rules of quantum chromodynamics. Every time you calculate how quarks should behave inside a neutron and compare the calculation to experiment, you are testing whether the theory is correct. So far, the theory has passed every test. The neutron's magnetic moment matches the QCD prediction. The neutron's mass matches. The neutron's lifetime, about 10 minutes when it is not bound inside a nucleus, matches the prediction for how long it should take one of the down quarks to decay into an up quark via the weak force. Everything fits, and yet there are still mysteries. The neutron's spin, for instance, is 1/2. That spin comes from the spins of the quarks and gluons inside, but the details are not what anyone expected. Measurements suggest that the valence quarks contribute only about 30% of the neutron's total spin. The rest comes from the spins of the gluons and the orbital motion of the quarks as they move around inside. That distribution was a surprise when it was first measured, and it is still not fully understood. Physicists call it the proton spin crisis, and the same crisis applies to the neutron. The spin is there. The total adds up, but the breakdown of where the spin comes from does not match the naive picture of 3 quarks spinning in a bag. The neutron is more complicated than that. The sea of quarks and gluons contributes. The structure matters. Quantum chromodynamics is not an easy theory. The math is hard. The predictions require supercomputers. The experiments require particle accelerators that cost billions of dollars. But the theory works. It explains why quarks are confined. It explains why protons and neutrons exist. It explains the neutron's magnetic moment, the thing that started this whole line of questioning back in the 1930s when Otto Stern measured a magnetic field coming from a particle that should not have one. The magnetic moment is not a paradox anymore. It is a consequence of the quark structure of the neutron and the constant churning interaction of quarks and gluons inside. The strong force is the most powerful force in nature at the scales where it operates. It is stronger than electromagnetism, stronger than the weak force, stronger than gravity by an absurd margin. And the full strength of that force is on display inside every atomic nucleus in your body. The neutron is held together by the strong force. The proton is held together by the strong force. The nucleus is held together by the residual strong force leaking out from the protons and neutrons inside it. Pull any of those pieces apart, and you release the energy that was stored in the gluon field holding them together. That is what happens in a nuclear explosion. The strong force, when unleashed, is catastrophic. But the strong force is not just destructive, it is creative. It built the elements. When stars fuse hydrogen into helium, they are fighting against electromagnetic repulsion and winning because the strong force takes over at short range. When massive stars explode in supernovae and forge carbon, oxygen, iron, and all the elements heavier than helium, the strong force is holding those new nuclei together long enough for them to survive and drift into space. The carbon in your bones, the oxygen in your lungs, the iron in your blood, all of it was created inside stars and held together by quantum chromodynamics. The same force that confines quarks inside a neutron is the force that built the periodic table. The neutron is not just a particle, it is a museum of the strong force, a tiny bound system where the rules of QCD are on full display if you know how to look. The magnetic moment was the clue, the crack in the surface, the first sign that the neutron was not what it appeared to be. And following that clue led to quarks, which led to gluons, which led to quantum chromodynamics, which led to a complete rethinking of what matter is and how it holds together. The neutron's magnetic field is not an accident, it is not a side effect. It is a direct, measurable consequence of the internal structure of the particle and the forces that bind that structure together. The magnetic moment is the neutron's signature, its fingerprint, the mark of the quarks and gluons churning inside. And if you want to see the strong force taken to its absolute limit, if you want to see what happens when magnetic fields are not just measurable but dominant, powerful enough to warp space and rip atoms apart, you do not look at neutrons sitting quietly inside nuclei. you look at neutron stars. And more specifically, you look at magnetars, dead stars where the magnetic field is so strong that the rules of physics start bending in ways that should not be possible. That is where the neutron story leads next, to the most extreme magnetic environments in the known universe. If you want to see the strong force taken to its absolute limit, if you want to see what happens when the magnetic properties of neutrons are not just measurable but dominant, powerful enough to warp space itself and tear matter apart, you do not look at individual neutrons sitting quietly inside atomic nuclei. You look at neutron stars. More specifically, you look at magnetars. Dead stars where the magnetic field is so strong that the rules of physics start bending in ways that should not be possible. Where the universe takes everything we just learned about the neutron's magnetic moment and scales it up by a factor so absurd that the result stops making intuitive sense. A magnetar is what happens when trillions upon trillions upon trillions of neutrons, each with its own tiny magnetic moment, get packed together so tightly that their individual fields add up into something that can rip atoms apart from 1,000 kilometers away. To understand magnetars, you have to start with neutron stars. And to understand neutron stars, you have to start with the death of something much larger. A massive star. Not our sun. Our sun is too small for this. Our sun will die quietly, puffing off its outer layers and leaving behind a white dwarf, a hot, dense ember about the size of Earth. That is a peaceful death. A neutron star is what happens when a star 10, 15, 20 times the mass of the sun reaches the end of its life and dies violently. When a massive star exhausts the fuel in its core, the fusion reactions that have been holding it up against its own gravity stop. The core collapses, and it does not collapse slowly. It collapses in less than a second. The entire core of a star, an object the size of Earth containing more mass than the sun, compresses down to a sphere about 20 kilometers wide. 20 kilometers, the size of a city. That is the neutron star. And the collapse releases so much energy that the outer layers of the star explode outward in a supernova, one of the brightest events in the universe. The flash can outshine an entire galaxy for weeks. The core that remains behind is silent, compact, and unimaginably dense. Here is how dense. A neutron star packs about 1.5 times the mass of the sun into a sphere 20 kilometers across. A tablespoon of neutron star material, if you could somehow scoop some out and bring it back to Earth, would weigh over 100 million tons. Not 100 million kilograms, 100 million tons. The weight of a mountain compressed into the volume of a sugar cube. The density is so extreme that atoms do not exist inside a neutron star. The electron clouds that normally surround atomic nuclei get crushed. The electrons merge with the protons in the nuclei, turning them into neutrons through a process mediated by the weak force. What you are left with is a ball of neutrons packed so tightly that they are almost touching. Neutron touching neutron, held up against further collapse only by something called neutron degeneracy pressure, a quantum mechanical effect that says you cannot pack fermions, particles like neutrons, with half-integer spin into the same quantum state. The neutrons resist further compression not because of any force in the traditional sense, but because the rules of quantum mechanics say they have to. If you could somehow compress a neutron star further, past the point where degeneracy pressure could hold it, the whole thing would collapse into a black hole. Neutron stars sit right on the edge of that limit. The typical neutron star spins fast. When the core of the massive star collapses, conservation of angular momentum kicks in. The same principle that makes an ice skater spin faster when they pull their arms in. The core was spinning slowly when it was the size of Earth. Compress it down to 20 kilometers, and it starts spinning hundreds of times per second. The fastest known neutron stars, called millisecond pulsars, rotate more than 700 times per second, 700 full rotations every second. A point on the surface of such a star is moving at a significant fraction of the speed of light. The star is not flying apart because gravity is holding it together with a grip so tight that nothing, not even the centrifugal force of spinning that fast, can overcome it. Most neutron stars have strong magnetic fields. The magnetic field of a typical neutron star is about 100 million to 1 trillion times stronger than Earth's magnetic field. That is already extreme. But magnetars take that number and push it into a completely different regime. A magnetar's magnetic field is about 1,000 to 10,000 times stronger than a regular neutron star's field. The strongest magnetar fields ever measured are on the order of 10 to the 15th Gauss, or about 1 billion Tesla. To put that in perspective, the strongest continuous magnetic field ever produced in a laboratory on Earth is around 45 Tesla. For a brief moment, using explosives to compress a magnetic field before the equipment destroys itself, experimentalists have reached fields of a few thousand Tesla. A magnetar sits at 1 billion Tesla, not for a fraction of a second, constantly, for thousands of years. At that field strength, the magnetic field is not just strong, it is dominant. It warps the vacuum of space, it distorts atoms, it bends the trajectories of photons. Within 1,000 kilometers of a magnetar, the magnetic field is so intense that it would rip the atoms in your body apart, not by heating you, not by crushing you, by pulling. The electrons in your atoms would feel a force so strong that they would be stripped away from the nuclei and dragged along the field lines. Your body would dissolve into a stream of ionized particles before you even got close. At a few hundred kilometers, the field is strong enough to distort the shapes of atoms themselves, stretching them into elongated needles aligned with the field. Quantum mechanics says atoms are supposed to be roughly spherical. The magnetar's field says otherwise. The field wins. Magnetars are rare. Only about 24 have been confirmed, and that number is probably close to the total in our galaxy. Most neutron stars do not become magnetars. The conditions required to produce a magnetic field that's strong are not entirely understood, but the leading theory involves the newborn neutron star's rotation. When a massive star collapses and forms a neutron star, the core is incredibly hot, on the order of 100 billion degrees. At those temperatures, the neutrons are not locked in place. They are in a fluid-like state, a superfluid in some regions, and the motion of charged particles in that fluid can generate powerful magnetic fields through a dynamo process. The same process that generates Earth's magnetic field, but scaled up to an environment where the fluid is unimaginably dense and the rotation rate is hundreds of times per second. If the newborn neutron star is spinning fast enough, somewhere between 100 and 1,000 times per second, the dynamo can amplify the magnetic field to magnetar levels within the first few seconds of the star's life. After that, the field is locked in. The neutron star cools, the fluid solidifies into a rigid crust, and the magnetic field is frozen into the structure of the star. The magnetic field does not stay frozen forever. It decays, slowly. The field is so strong that it stores an enormous amount of energy, and that energy has to go somewhere. Over the course of about 10,000 years, the magnetic field gradually weakens, and the energy is released as radiation. X-rays, gamma rays, heat. This is what makes magnetars visible. They glow. Not because they are hot in the traditional sense. A neutron star cools quickly after it forms, and by the time it is a few thousand years old, its surface temperature has dropped to a few million degrees, which sounds hot but is actually cool for a neutron star. The glow from a magnetar does not come from heat, it comes from the magnetic field. The decaying field accelerates charged particles, and those particles emit high-energy radiation, X-rays primarily, but during violent events, gamma rays. The magnetar is powered by its own magnetic field, and that field is eating itself. The magnetic field also exerts stress on the star's crust. The crust of a neutron star is not uniform. It is made of nuclei arranged in a crystalline lattice, a solid structure not unlike the crystal structure of metals on Earth, but compressed to densities where nuclei are packed so close together that they almost touch. The magnetic field threads through this crust, and as the field evolves and shifts, it exerts forces on the lattice. Twist the field, and you twist the crust. Shear the field, and you shear the crust. If the stress builds up too much, the crust fractures, the lattice breaks. Chunks of crust, each containing more mass than a mountain, shift suddenly by a few millimeters. That shift releases energy, a lot of energy. The event is called a starquake, and it is one of the most violent seismic events in the universe. When a magnetar's crust fractures, the magnetic field reconfigures almost instantaneously. Field lines snap and reconnect, a process that releases a burst of high-energy radiation. The burst lasts a fraction of a second, but in that fraction of a second, the magnetar emits as much energy as the sun emits in 100,000 years. The radiation is mostly in the gamma-ray range, and the burst is so bright that it can be detected across the galaxy. Astronomers call these events soft gamma repeaters because the bursts repeat. A magnetar does not have just one starquake. It has many, spread out over years or decades. Each starquake is a reconfiguration of the magnetic field, a step in the long, slow decay toward a quieter state. In December of 2004, a magnetar called SGR 1806-20, located about 50,000 light-years from Earth, produced the largest burst ever recorded. The burst lasted about 1/10 of a second, and in that 1/10 of a second, it released about 10 to the 46 ergs of energy. That is more energy than the sun has emitted in the entire history of its existence so far. The burst was so bright that it saturated detectors on satellites across the solar system. It ionized the upper atmosphere of Earth, causing a measurable change in the propagation of radio waves. The magnetar was 50,000 light-years away. If it had been 10 light-years away, the distance to the nearest stars, the burst might have been strong enough to strip away part of Earth's ozone layer and trigger a mass extinction. Magnetars are dangerous even at interstellar distances. The magnetic field of a magnetar is so strong that it affects the star's rotation. As the field decays, it exerts a braking torque on the star, slowing it down. Most magnetars spin much slower than regular pulsars. A typical magnetar rotates once every few seconds, sometimes once every 10 seconds. That is slow for a neutron star. The field is acting like a brake, sapping the rotational energy and converting it into radiation and heat. Over time, the magnetar spins down, the field weakens, and the bursts become less frequent. Eventually, after about 10,000 years, the magnetar's field has decayed to the point where it is no longer distinguishable from a regular neutron star. The magnetar phase is temporary. It is a brief, violent stage in the life of a neutron star, a period where the magnetic field dominates everything and the star announces its presence to the galaxy with bursts of gamma rays. The connection between magnetars and the neutron's magnetic moment is direct. The magnetic field of a magnetar is generated by the collective behavior of the neutrons inside the star. Each neutron has a magnetic moment of about -1.913 nuclear magnetons. That is a tiny number. A single neutron's magnetic field is far too weak to measure unless you are using extremely sensitive equipment. But inside a magnetar, there are about 10 to the 57 neutrons. 10 to the 57, that is a 1 with 57 zeros after it. Most of those neutrons are not aligned. Their magnetic moments point in random directions and they cancel out. But in the presence of a strong external field, or in a region where the field is being generated by a dynamo process, a small fraction of the neutrons can become partially aligned. Even a tiny net alignment, just a fraction of a percent, is enough. When you multiply that tiny fraction by 10 to the 57, you get a macroscopic magnetic field, a field strong enough to dominate the behavior of the entire star. The exact mechanism by which magnetars generate and sustain such extreme fields is still debated. The dynamo model is the leading candidate, but the details are not settled. Some models suggest that the field is generated in the first few seconds after the neutron star forms, when the core is still fluid and rotating rapidly. Other models suggest that the field is generated later, as the star cools and crystallizes through a process involving the motion of superconducting protons in the core. Protons inside a neutron star are not free protons. They are mixed in with the neutrons, and at the temperatures and densities inside the star, they form a superconducting fluid. A superconductor has zero electrical resistance, which means currents can flow through it indefinitely without dissipating. If you can set up a current in a superconductor, that current will keep flowing, and it will generate a magnetic field that persists as long as the superconductor remains superconducting. Inside a magnetar, the superconducting protons could be carrying enormous persistent currents, and those currents could be the source of the magnetic field. Either way, the field is there, and it is real. Observations confirm it. Magnetars emit X-rays with a spectrum that matches the predictions for radiation emitted by charged particles spiraling along magnetic field lines in fields of about 10 to the 15 Gauss. The rotation periods of magnetars slow down at a rate consistent with magnetic braking from fields of that strength. The bursts they emit have energies and timescales that match models of magnetic field reconnection and crustal fractures driven by magnetic stress. Every piece of data points to the same conclusion. The magnetic field is as strong as the models say it is, and that field is the defining feature of the star. Magnetars are also candidates for the source of fast radio bursts, or FRBs. Fast radio bursts are brief pulses of radio emission lasting a few milliseconds that appear randomly across the sky. They were discovered in 2007, and for years no one knew what was causing them. The bursts are extremely bright enough to be detected from billions of light years away, but they happen so quickly that pinpointing their source is difficult. In 2020, astronomers detected a fast radio burst from a magnetar inside our own galaxy. The magnetar, called SGR 1935+2154, emitted a burst of radio waves during an X-ray flare. The radio burst had all the characteristics of the extragalactic fast radio bursts: brightness, duration, frequency range. The match was close enough that most astronomers now believe at least some fast radio bursts are coming from magnetars in other galaxies. The bursts are likely associated with starquakes or magnetic reconnection events, violent reconfigurations of the field that accelerate particles to relativistic speeds and produce a brief flash of coherent radio emission. The magnetic field of a magnetar is strong enough to affect the propagation of light. Photons traveling through a strong magnetic field experience a phenomenon called vacuum birefringence. In a normal vacuum, light travels in straight lines at a constant speed, and the polarization of the light does not change. In the vacuum near a magnetar, the magnetic field is so strong that it distorts the quantum vacuum itself, creating virtual electron-positron pairs that interact with passing photons. The result is that the speed of light depends slightly on the polarization of the photon. Light polarized parallel to the magnetic field travels at a slightly different speed than light polarized perpendicular to the field. This splits the light into two beams with different polarizations, hence birefringence. The effect is tiny, but it has been detected in the X-ray emission from magnetars. The polarization of the X-rays changes as the light passes through the magnetar's magnetic field, and the observed polarization pattern matches the predictions of quantum electrodynamics in strong magnetic fields. The field is so strong that it makes the vacuum behave like a material with optical properties. Magnetars also exhibit something called quantum electrodynamic cascades. When a charged particle, such as an electron, moves through a strong magnetic field, it emits photons. In a weak field, the particle loses a little energy and continues on its way. In a magnetar's field, the photon carries so much energy that it can spontaneously convert into an electron-positron pair. The newly created pair then moves through the field, emits more photons, which convert into more pairs, and the process cascades. One particle becomes two, two become four, four become eight, and so on. The cascade continues until the particles lose enough energy that the photons can no longer create pairs. This process is called pair production, and it is a standard prediction of quantum electrodynamics. But in most environments, pair production requires very high energy photons, the kind you get near black holes or in particle accelerators. In a magnetar's field, the field itself provides the energy. The magnetic field is so strong that it lowers the threshold for pair production, allowing cascades to develop from relatively low-energy seed particles. The cascades fill the magnetar's magnetosphere with a dense plasma of electrons and positrons, and that plasma is what emits the X-rays and gamma rays we detect. The strength of a magnetar's field can be inferred from the star's spin-down rate. Neutron stars lose rotational energy over time, and the rate at which they slow down depends on how much energy is being carried away by radiation and magnetic braking. For a typical pulsar, the spin-down is caused mostly by the emission of electromagnetic radiation and relativistic particles from the star's magnetic poles. For a magnetar, the spin-down is much faster because the magnetic field is so strong that it exerts a powerful braking torque. By measuring the star's rotation period and how quickly that period is increasing, astronomers can calculate the strength of the magnetic field. The results are consistent across multiple magnetars, fields of 10 to the 14th to 10 to the 15th Gauss. Some magnetars show evidence of even stronger internal fields, possibly up to 10 to the 16th Gauss in the deep interior. Though those fields are not directly observable, the surface field is what we measure, and it is already stronger than anything else in the universe. Magnetars represent the extreme end of what is possible for a neutron star. They are the result of a very specific set of conditions during the star's formation, conditions that favor the amplification of the magnetic field to levels that dominate the star's entire life cycle. Most massive stars that explode in supernovae do not produce magnetars. They produce regular neutron stars, or they produce black holes if the core is too massive. The fact that magnetars exist at all is a sign that the universe has a way of exploring the full range of possibilities. Given enough stars, enough supernovae, enough chances, even the rare outcomes eventually happen. And when they do, they produce objects so extreme that they challenge our understanding of physics. The neutron, with its magnetic moment of -1.913 nuclear magnetons, is the building block of all of this. Without that magnetic moment, without the internal structure of quarks and gluons that produces it, neutron stars would not have magnetic fields. Magnetars would not exist. The bursts of gamma rays, the starquakes, the fast radio bursts, all of it depends on the fact that neutrons are not magnetically inert. The neutron's magnetic moment, the thing that Otto Stern measured in the 1930s, scales up. Take 10 to the 57 neutrons, pack them into a sphere 20 kilometers wide, spin the sphere hundreds of times per second, and the magnetic moments add up into a field strong enough to distort spacetime and rip matter apart. The universe took a property that seems insignificant at the level of a single particle and turned it into one of the most violent phenomena we have ever observed. And yet, even with everything we have learned about the neutron's magnetic moment, even with the Quark model and quantum chromodynamics and the detailed calculations of how quarks contribute to the neutron's properties, there is still a puzzle. A puzzle that sits right at the center of the neutron's identity. The neutron has spin 1/2. That spin comes from the quarks and gluons inside. But when physicists tried to add up the contributions from all the pieces, they found that the numbers did not match. The quarks, it turned out, were contributing less than half of the neutron's total spin. The rest was coming from somewhere else, from the gluons, from the orbital motion of the quarks, from the sea of virtual particles churning inside. The breakdown did not make sense. And that puzzle, which emerged in the late 1980s and is still not fully resolved, has a name: the proton spin crisis. And it applies to the neutron just as much as it applies to the proton. Because if we do not understand where the neutron's spin comes from, then we do not fully understand the neutron. And that means there is still more to learn. Here is the problem with understanding where the neutron gets its magnetic moment. Once you accept that the neutron is made of quarks, and that those quarks have spins and charges that generate magnetic fields, you would think the story is over. You add up the spins, multiply by the charges, account for how the quarks are moving around inside, and you get the magnetic moment. Done. The math works. The prediction matches the measurement. The neutron's magnetic moment comes from the quarks inside. Case closed, except it is not that simple. Because once physicists started looking closely at where the spin itself comes from, the numbers stopped adding up. Not the magnetic moment this time. The spin. The intrinsic angular momentum of the neutron, the property that determines how the particle behaves in a magnetic field and defines half of what it means to be a fermion. The neutron has a spin of 1/2. That is a fixed, measurable, undeniable fact. The question is where that spin comes from. And when experimentalists tried to break it down into pieces, tried to figure out how much of the neutron's spin came from the quarks and how much came from everything else, they found something deeply uncomfortable. The quarks were contributing far less than they should, by a lot. This puzzle is called the proton spin crisis, and despite the name, it applies to the neutron just as much as it does to the proton. Both particles are nucleons. Both are built from 3 valence quarks held together by gluons. Both have spin 1/2, and in both cases, the spin does not come from where the simplest models said it should. The crisis was not that the proton or the neutron had the wrong spin. They do not. The spin is exactly 1/2 as measured. The crisis was that when you tried to figure out where that spin was coming from, the answer you got back from experiment was inconsistent with the most basic assumption anyone had made about how quarks work. Before 1987, the assumption was straightforward. The proton is made of 2 up quarks and 1 down quark. Each quark has a spin of 1/2. Combine 3 quarks, and their spins should add up to give the proton its total spin. The math is a little more complicated than just adding 1/2 plus 1/2 plus 1/2, because spins are quantum mechanical objects and they combine according to specific rules. But the basic picture was clear. The 3 valence quarks are spinning. Their spins combine to give the proton a net spin of 1/2. Most of the proton's spin should come from the spins of its quarks. That was the naive expectation, and for years nobody questioned it. It made sense. It fit the Quark model. It should have been right. Then the European Muon collaboration, usually shortened to EMC, performed an experiment that shattered that assumption. The experiment took place at CERN in the mid-1980s. The setup was conceptually similar to the deep inelastic scattering experiments that had confirmed the existence of quarks in the first place. Fire a beam of high-energy particles at a proton target and watch how they scatter. Measure the angles, the energies, the directions, and you can infer what is happening inside the proton. But this time there was a twist. Both the beam and the target were polarized. That means the spins of the particles in the beam were aligned in a specific direction, and the spins of the protons in the target were also aligned. Polarized scattering gives you information that unpolarized scattering does not. It lets you measure not just how many quarks are inside the proton, but how those quarks are spinning, whether their spins are aligned with the proton's spin, or opposite to it, or pointing in some other direction. The EMC collaboration used a beam of polarized muons. Muons are heavy cousins of the electron, and like electrons, they scatter off quarks through the electromagnetic force. When a muon slams into a quark inside a proton, it exchanges a virtual photon with the quark, and the muon deflects. By measuring how the scattering rate depends on the polarization of the beam and the target, you can extract a quantity called the quark spin contribution. This quantity tells you how much of the proton's total spin comes from the spins of the quarks inside. If the naive picture were correct, that contribution should be close to 1, close to 100%. The quarks should account for essentially all of the proton's spin. In 1987, the EMC published their result. The quark spin contribution was not close to 1, it was close to 0. The exact number depended on how you analyzed the data, and the uncertainties were large, but the central value was consistent with the quarks contributing somewhere between 4 and 24% of the proton's spin, not most of it, a small fraction. The result was so unexpected that many physicists initially assumed there had been a mistake. The experiment was reanalyzed, the data was checked. Independent groups looked at the same scattering events using different techniques. The result held. The quarks inside the proton were not carrying the proton's spin, or at least they were carrying far less of it than anyone had expected. The term proton spin crisis was coined shortly after. Crisis might sound dramatic, but it was an accurate description of how the result was received. The Quark model had explained so much. It had organized the particle zoo. It had predicted masses, charges, decay rates, magnetic moments. It had survived every test thrown at it for more than 20 years. And now, suddenly, one of its most basic predictions, that the spins of the quarks should add up to the spin of the proton, was wrong. Not slightly wrong, badly wrong. The discrepancy was not a few percent. It was on the order of 60 to 70%. More than half of the proton's spin was missing. It had to be somewhere, but the quarks were not providing it. The neutron, by extension, had the same problem. The neutron is 2 down quarks and 1 up quark. Same rules, same quantum mechanics, same spin structure. If the quarks in the proton were not carrying the proton's spin, then the quarks in the neutron were not carrying the neutron's spin either. The crisis was not limited to one particle. It was a fundamental challenge to the way physicists understood the internal structure of all nucleons. Here is why the result was so shocking. Spin is a conserved quantity. If the proton has spin 1/2, that spin has to come from somewhere. It cannot just appear out of nowhere. The proton is made of quarks and gluons, and those are the only ingredients available. So the spin has to be carried by the quarks, the gluons, or the motion of the quarks and gluons as they move around inside the proton. There is no other option. The EMC results said the quarks were contributing only a small fraction, so the rest had to be coming from the gluons or from the orbital motion, or both. But in the mid-1980s, nobody had measured the gluon contribution. Nobody had measured the orbital contribution. The only thing anyone had measured was the quark contribution, and it was far too small. The immediate response was to look for the missing spin in the gluons. Gluons carry the strong force, and they are constantly being exchanged between quarks inside the proton. Gluons have spin 1, which means they are bosons, not fermions, and their spins can add up differently than quark spins. If the gluons inside the proton were polarized, if their spins were aligned in a specific direction, they could contribute to the proton's total spin. The question was how much. Theoretical models suggested the gluon contribution could be significant, maybe even large enough to explain the missing spin. But measuring it was hard. Gluons do not carry electric charge, so they do not interact directly with the electromagnetic probes that experimentalists had been using to study quarks. You cannot scatter an electron off a gluon and measure the deflection. You have to use indirect methods, and those methods require different experiments. One of the key facilities for studying gluon spin has been the Relativistic Heavy Ion Collider, or RHIC, located at Brookhaven National Laboratory in New York. RHIC is a particle accelerator designed to collide heavy ions like gold nuclei at extremely high energies. But it can also collide protons, and more importantly, it can collide polarized protons, protons whose spins are aligned. By smashing polarized protons together and studying what comes out, physicists can measure how the gluons inside those protons are polarized. The technique is called polarized proton-proton scattering, and it has been one of the main tools for probing the gluon contribution to nucleon spin. The results from RHIC, accumulated over the past 2 decades, have confirmed that gluons do contribute to the proton's spin. The contribution is not negligible. Estimates vary depending on the details of the analysis and the energy range being probed, but the gluon spin contribution appears to be somewhere in the range of 25 to 50% of the total spin. That is significant. It is not enough to fully explain the missing spin on its own, but it is a large enough fraction that it cannot be ignored. Gluons are part of the story. They always were. The naive picture that ignored them was incomplete. In 2023, the Phoenix experiment at RHIC published results showing that gluon spins inside the proton are preferentially aligned with the proton's spin. Not perfectly aligned, not all of them, but enough that there is a net contribution. The gluons are not just sitting there, spinning in random directions. They have a preferred orientation, and that orientation is correlated with the proton's overall spin. This was an important confirmation. It showed that the gluons are not passive bystanders. They are active participants in the spin structure of the proton. But even with the gluon contribution included, the numbers still do not add up perfectly. Quarks contribute about 30 to 40%. Gluons contribute another 25 to 50%, depending on whose measurement you trust. Add those together and you get somewhere in the range of 55 to 90%. That is closer to 100% than the original EMC result, but it is still not a complete accounting. There is still a gap, and the current consensus is that the remaining spin comes from orbital angular momentum. The quarks and gluons inside the proton are not sitting still. They are moving. They are orbiting around each other, circulating through the interior of the proton in complex patterns that change from moment to moment. That motion carries angular momentum, and that angular momentum contributes to the proton's total spin. Orbital angular momentum is a standard concept in quantum mechanics. An electron orbiting a nucleus in an atom has orbital angular momentum. A planet orbiting a star has orbital angular momentum. The idea is not new, but applying it to quarks inside a proton is tricky, because the quarks are not orbiting in simple circular paths the way planets do. They are confined by the strong force, which creates a constantly shifting, dynamic environment. The quarks are moving, but the motion is not smooth. It is chaotic, turbulent, driven by the exchange of gluons and the constant creation and annihilation of virtual quark-antiquark pairs. Calculating the orbital contribution requires sophisticated theoretical models and numerical simulations on supercomputers. It is not something you can measure directly in an experiment. You have to infer it from what is left over after you have measured everything else. By 2008, theoretical work had advanced far enough that a detailed paper was published arguing that more than half of the proton's spin came from the spins of the quarks, with the missing part supplied by the orbital angular momentum of the quarks. This was a shift from earlier interpretations which had suggested the quark spin contribution was much smaller. The difference came down to how you define the contributions. Spin in quantum field theory is not as simple as it sounds. You can split the total angular momentum of a system into pieces in different ways, depending on which mathematical framework you use. Different frameworks give different breakdowns. The total spin is always the same, 1/2 for the proton and the neutron. But how much you assign to quark spin versus gluon spin versus orbital motion depends on your choice of decomposition. That ambiguity has made it difficult to settle the spin crisis definitively. Physicists are not arguing about the total spin. They are arguing about how to divide it up into pieces in a way that is both mathematically consistent and physically meaningful. Lattice quantum chromodynamics has become one of the most powerful tools for addressing this question. Lattice QCD is a technique where space and time are divided into a grid of discrete points, and the equations of quantum chromodynamics are solved numerically on that grid using supercomputers. The method is computationally expensive, but it allows physicists to calculate properties of protons and neutrons directly from the fundamental theory without making simplifying assumptions. By 2017, lattice QCD simulations were producing results that suggested the quark spin contribution should be about 30% of the total spin, with the rest coming from gluons and orbital motion. That number is broadly consistent with experimental measurements, and it has helped narrow the range of uncertainty. Shangdong Ji, a theoretical physicist who has been one of the leading voices in the effort to resolve the spin crisis, pointed out in 2017 that the lattice results support the idea that quark spin contributes roughly 1/3 of the nucleon spin, not 100%, as the naive picture suggested, not 0, as the earliest EMC results seem to imply, 1/3. A significant fraction, but not the dominant contribution. The rest comes from the gluons and the orbital motion, and disentangling those two contributions is the focus of current research. The proton spin crisis was never really about the proton being broken or quantum chromodynamics being wrong. It was about the failure of the simplest possible picture. The picture where you treat the proton as a bag of 3 quarks and ignore everything else. That picture works for some properties, like electric charge. Add up the charges of the quarks and you get the charge of the proton. Done. But spin is more complicated. Spin depends not just on the number of quarks and their individual spins, but on how those quarks are moving, how the gluons are contributing, and how the entire system is organized dynamically. The proton is not a static object. It is a quantum mechanical bound state where everything is constantly fluctuating and interacting. The spin comes from all of those interactions, not just from the quarks sitting still and spinning in place. The same lesson applies to the neutron. The neutron's spin is 1/2. That spin comes from the 2 down quarks and 1 up quark inside, from the gluons binding them together, and from the orbital motion of the quarks and gluons as they circulate through the neutron's interior. The breakdown is probably similar to the protons. Quarks contribute about 30 to 40%. Gluons contribute another chunk. Orbital motion makes up the rest. The exact numbers are still being refined, and they depend on the energy scale at which you probe the neutron and on the theoretical framework you use to define the contributions. But the broad picture is clear. The spin is distributed. It is not localized in one component. It is a collective property of the entire system. One of the reasons the spin crisis took so long to emerge is that spin is harder to measure than charge or mass. Charge shows up immediately in scattering experiments. Mass determines the energy levels of bound states. Spin requires polarized beams, polarized targets, and careful analysis of how scattering rates depend on the relative orientations of the spins. Those techniques were not available in the early days of particle physics. By the time they were, the quark model was so well established that most physicists assumed the spin question had already been answered. It had not. The crisis also revealed gaps in the way physicists communicate what a theory predicts. The quark model, as originally formulated, did not explicitly predict that quark spins should account for 100% of the nucleon spin. It just did not say otherwise. The model focused on quantum numbers like charge and flavor and mass, properties that could be calculated by adding up the contributions of the valence quarks. Spin was assumed to work the same way, but that assumption was never rigorously tested. When the EMC experiment finally tested it, the assumption turned out to be wrong. There is a broader lesson here about how science works. Theories are built on assumptions, and those assumptions are usually reasonable at the time they are made. But every assumption is a potential point of failure, a place where the theory might break down or where the picture might be incomplete. The quark model was not wrong, it was incomplete. It described the valence quark content of the proton and the neutron accurately, but it did not capture the full complexity of the internal dynamics. Adding gluons and orbital motion to the picture was not a correction to the quark model, it was a refinement, a recognition that nucleons are not simple systems and that understanding them fully requires accounting for all the moving parts. The ongoing effort to resolve the spin crisis involves experiments at facilities around the world. RHIC continues to collide polarized protons and measure how gluons contribute to spin. The Thomas Jefferson National Accelerator Facility, also known as Jefferson Lab, uses polarized electron beams to study the internal structure of protons and neutrons in exquisite detail. The Electron-Ion Collider, a new facility under construction at Brookhaven, is designed specifically to probe the spin structure of nucleons at higher energies and with better precision than any previous experiment. When it comes online in the early 2030s, it will provide the most detailed picture yet of how quarks, gluons, and orbital motion contribute to nucleon spin. Theoretical work continues in parallel. Lattice QCD simulations are becoming more refined as supercomputers get faster and algorithms improve. Theorists are developing new ways to decompose the total angular momentum into physically meaningful pieces. The goal is not just to match the experimental numbers. The goal is to understand, at a fundamental level, how the spin of a composite particle emerges from the spins and motions of its constituents. That understanding would be a major step forward in the effort to fully describe the strong force and the behavior of matter at the smallest scales. The proton spin crisis, despite its name, is not really a crisis anymore. It is a puzzle, a question with partial answers and ongoing research. The total spin is known. The rough contributions from quarks, gluons, and orbital motion are understood. The details are still being worked out, but the broad picture is no longer shocking. It is just complicated. Which, given that we are talking about the internal structure of a particle smaller than an atom, held together by one of the most powerful forces in nature, should not be surprising. The neutron sits at the center of all of this. Its magnetic moment comes from the spins and charges of the quarks inside. Its spin comes from the quarks, the gluons, and the orbital motion of both. Its mass comes from the energy stored in the gluon field. Its stability, or lack of it when free, comes from the weak force acting on one of the quarks inside. Every property of the neutron is a window into the rules of quantum chromodynamics, and every measurement of those properties is a test of whether we understand those rules. The spin crisis showed that we did not understand as much as we thought we did. The resolution of the crisis is showing that the neutron is more interesting than we imagined, and there is still more. Because even after accounting for the magnetic moment and the spin and the mass and the forces holding everything together, there is another property of the neutron that physicists have been trying to measure for decades. A property that should exist according to the simplest extensions of the standard model, but has never been detected. A property so small that finding it would require the most sensitive experiments ever built. And if it turns out to be larger than the standard model predicts, if it shows up at a level that cannot be explained by known physics, it would be a direct sign that something new is happening inside the neutron. Something that could explain why the universe exists at all. That property is called the electric dipole moment, and the search for it is one of the most important experiments in particle physics today. Here is where the story gets uncomfortable, because after decades of measuring the neutron's magnetic moment, after building an entire theory of quarks and gluons to explain it, after probing the neutron's spin structure and finding that it is distributed across quarks, gluons, and orbital motion, physicists started asking a different question, a question that should have had a boring answer. A question that, if it turns out to have an interesting answer, would crack open the standard model and force us to rewrite our understanding of why the universe looks the way it does. The question is this: does the neutron have an electric dipole moment? To understand why that question matters, you need to understand what a dipole moment is. Take a bar magnet. It has a north pole and a south pole. The two poles are separated in space, and the separation creates a magnetic dipole moment. The strength of the moment depends on how strong the poles are and how far apart they sit. A magnetic dipole moment is a measure of how lopsided the magnetic field is. All magnets have one. The neutron has one. We have spent the last several chapters explaining how and why. An electric dipole moment is the same idea, but with electric charge instead of magnetism. Take a molecule like water. The oxygen atom pulls electrons toward itself more strongly than the hydrogen atoms do. So the oxygen end of the molecule is slightly negatively charged, and the hydrogen end is slightly positively charged. The charges do not cancel at a single point, they are separated. That separation creates an electric dipole moment. The molecule has no net charge. Positive and negative still add to zero, but the positive charge and the negative charge are not sitting in the same place, and that spatial separation gives the molecule an electric dipole moment. You can measure it. You can calculate its strength. It shows up in how the molecule behaves in an electric field. Now apply that idea to the neutron. The neutron has no net electric charge. We have established that. The charges of the quarks inside, positive 2/3 from the up quark and negative 1/3 from each of the two down quarks, add up to zero, but the quarks are not sitting on top of each other. They are spread out over a region of space about 1 femtometer across. So the question is whether the positive charge and the negative charge inside the neutron are distributed symmetrically, or whether there is a slight offset. If the center of positive charge and the center of negative charge are separated even by a tiny amount, the neutron would have an electric dipole moment, a measure of how lopsided the internal charge distribution is. For most of the 20th century, physicists assumed the electric dipole moment of the neutron was zero. Not approximately zero, exactly zero. The assumption was based on symmetry, specifically a symmetry called CP symmetry, which stands for charge parity symmetry. CP symmetry is one of the fundamental symmetries of particle physics, and it says that the laws of physics should look the same if you swap all particles with their antiparticles and flip space into its mirror image. Charge conjugation, C, swaps particles and antiparticles. Parity, P, flips left and right. Combine them and you get CP. If CP symmetry is exact, if the universe respects it perfectly, then certain properties of particles are forbidden. One of those properties is a permanent electric dipole moment for particles like the neutron. Here is why. An electric dipole moment has a direction. It points from the negative charge toward the positive charge. But the neutron also has spin, and spin has a direction. If the neutron has an electric dipole moment, that moment has to be aligned either parallel or antiparallel to the neutron's spin. There is no other option. The dipole moment is an intrinsic property of the particle, just like the spin, and intrinsic properties cannot point in arbitrary directions. They have to align with the particle's internal structure. So the electric dipole moment, if it exists, points either along the spin axis or opposite to it. Now apply the CP transformation. Charge conjugation flips the sign of all charges, so it flips the direction of the electric dipole moment. Positive becomes negative, negative becomes positive, and the dipole flips around. Parity flips space, but it does not flip spin. Spin is an axial vector, a mathematical object that behaves differently under parity than regular vectors. When you flip space, the spin stays pointing in the same direction, so after a CP transformation, the electric dipole moment has flipped, but the spin has not. The dipole is now pointing in the opposite direction relative to the spin. If CP symmetry is exact, the neutron before the transformation and the neutron after the transformation should be indistinguishable, but they are not. One has the dipole aligned with the spin, the other has it anti-aligned. The only way to make them indistinguishable is if the dipole moment is zero. No dipole, no problem. CP symmetry demands that the neutron's electric dipole moment is exactly zero. That was the assumption for decades. And then, in 1964, James Cronin and Val Fitch performed an experiment that showed CP symmetry is not exact. It is violated, not by a lot, not in every process, but in certain rare decays of particles called neutral kaons, CP symmetry breaks down. The kaons do not behave the same way as their CP-transformed counterparts. The universe does not respect CP symmetry perfectly. Cronin and Fitch won the Nobel Prize in 1980 for the discovery, and the result sent a shockwave through the field. If CP is violated in kaon decays, it could be violated elsewhere, including, potentially, in the internal structure of the neutron. A non-zero neutron electric dipole moment would be a direct signal of CP violation. It would mean the charge distribution inside the neutron is not symmetric under the CP transformation. The positive and negative charges are not arranged in a way that looks the same when you swap particles for antiparticles and flip space. The neutron would have a preferred direction, a built-in asymmetry that points along its spin axis. That asymmetry would be tiny, almost certainly too small to affect anything in everyday life, but it would be there. And finding it would tell us that the neutron, and by extension the quarks and gluons inside it, are subject to CP-violating forces that we do not fully understand yet. Here is where this gets important. The fact that the universe is made of matter and not antimatter is one of the biggest unsolved problems in physics. When the universe began, the Big Bang should have created equal amounts of matter and antimatter, particles and antiparticles, for every quark an antiquark, for every electron a positron. Matter and antimatter annihilate when they meet, turning into pure energy. If the early universe started with equal amounts of both, they should have annihilated each other completely, leaving behind a universe filled with nothing but radiation, no atoms, no stars, no planets, no us. But that is not what happened. Somehow, the universe ended up with slightly more matter than antimatter, roughly one extra matter particle for every billion matter-antimatter pairs. The antimatter annihilated with most of the matter, and the tiny leftover excess became everything we see today. Every galaxy, every star, every atom in your body, all of it came from that small imbalance. The process that could have created that imbalance is called baryogenesis, and it requires three conditions, first laid out by the physicist Andrei Sakharov in 1967. First, the laws of physics must violate baryon number conservation. Baryon number is a quantum number that counts the difference between the number of baryons, particles like protons and neutrons, and antibaryons. If baryon number is conserved, you cannot create more baryons than antibaryons. The universe would stay balanced. Second, the laws must violate C symmetry and CP symmetry. If the universe treated particles and antiparticles identically, any process that created extra matter would also create extra antimatter, and you would end up back where you started. CP violation is necessary to tip the scales. Third, the universe must have been out of thermal equilibrium at some point in its early history. If everything were in equilibrium, matter and antimatter would have stayed balanced, no matter what else was happening. You need a period where the universe was changing fast enough that different processes could not keep up with each other. We know the third condition is met. The universe has been expanding and cooling since the Big Bang, and during certain phases, particularly right after the electro-weak phase transition, the universe was definitely out of equilibrium. We have hints that the first condition might be met. Baryon number violation is predicted by certain extensions of the Standard Model, and there are processes in the early universe that could have violated it. But the second condition, CP violation, is the tricky one. We know CP violation exists. Cronin and Fitch proved it. We know it shows up in kaon decays and in decays of particles called B mesons. But the amount of CP violation we have observed so far is not enough. The standard model includes CP violation through something called the CKM matrix, a mathematical object that describes how quarks of different types mix and transform into each other. The CKM matrix predicts a small amount of CP violation, and that prediction matches the experimental results for kaons and B mesons. But when you plug the CKM matrix into models of baryogenesis and try to calculate how much matter-antimatter asymmetry it can produce, the answer comes out about 10 orders of magnitude too small. Not close, nowhere near close. The CP violation we know about cannot explain why the universe is made of matter. That means there has to be more, some additional source of CP violation that we have not discovered yet. Something beyond the standard model. And one of the places that new CP violation could show up is in the neutron's electric dipole moment. If the neutron has a non-zero electric dipole moment that is larger than the standard model predicts, it would be a sign that there are new CP violating interactions happening inside the neutron. Interactions involving particles or forces we have not detected yet. Those interactions could be the missing piece of the baryogenesis puzzle. They could be the reason you exist. This is not speculation. This is one of the primary motivations for measuring the neutron's electric dipole moment. Physicists are not just trying to test CP symmetry for its own sake. They are trying to understand why the universe contains matter. The neutron is one of the best places to look for new CP violation because it is a composite particle made of quarks held together by the strong force, and both the quarks and the strong force could be affected by whatever new physics is generating the extra CP violation. The neutron is a laboratory, a probe, a window into processes that happened in the first fraction of a second after the Big Bang. The challenge is that the expected size of the neutron's electric dipole moment is extraordinarily small. The standard model predicts a value of about 10 to the negative 32 electron centimeters. That is 32 orders of magnitude smaller than the size of an atom. To put that in perspective, if you scaled an atom up to the size of Earth, the standard model prediction for the neutron's electric dipole moment would be smaller than the width of a human hair. It is not just small, it is unimaginably, absurdly, almost insultingly small. No experiment currently running or planned for the next decade can measure something that tiny. The standard model prediction is effectively zero for all practical purposes. But many theories beyond the standard model predict values that are larger, not large, still tiny, but within the range of what a sufficiently sensitive experiment might detect. Supersymmetry, for instance, a theory that proposes a new symmetry between fermions and bosons and predicts a whole zoo of new particles, generically predicts neutron electric dipole moments in the range of 10 to the negative 28 to 10 to the negative 26 electron centimeters. That is still small, but it is 6 orders of magnitude larger than the standard model prediction, and it is in the range where current experiments are starting to probe. Other theories involving extra dimensions or new forces or particles that interact with the Higgs field in unusual ways make similar predictions. If any of those theories are correct, the neutron's electric dipole moment is sitting right on the edge of detectability, just barely out of reach, waiting. The current experimental upper limit on the neutron's electric dipole moment is less than 1.8 times 10 to the negative 26 electron centimeters. That number comes from an experiment that ran from 2000 to 2016 at the Paul Scherrer Institute in Switzerland. The experiment has not detected a dipole moment. What it has done is set an upper limit. If the dipole moment exists, it has to be smaller than that number. Every time an experiment runs and finds nothing, it sets a tighter upper limit, shrinking the range where new physics could be hiding. Here is how you measure something that small. First, you need neutrons, lots of them, and not just any neutrons. You need ultra-cold neutrons, neutrons that have been slowed down so much that they are barely moving. A thermal neutron, the kind you get from a nuclear reactor, moves at about 2,000 meters per second. An ultra-cold neutron moves at about 5 meters per second, walking speed. The reason you want slow neutrons is that slow neutrons can be trapped. If you put an ultra-cold neutron inside a container made of certain materials, like certain types of metal or glass, the neutron will bounce off the walls rather than passing through them. You can store ultra-cold neutrons in a bottle for minutes at a time, long enough to measure their properties with extreme precision. Once you have a bottle full of ultra-cold neutrons, you apply a strong, uniform magnetic field. The neutrons have magnetic moments, so they precess in the magnetic field. Precession is the same motion a spinning top makes when it wobbles. The spin axis of the neutron does not stay fixed. It rotates slowly around the direction of the magnetic field. The rate of precession depends on the strength of the field and the size of the neutron's magnetic moment. You can measure the precession rate by watching how the neutron spins evolve over time. Now here is the trick. If the neutron also has an electric dipole moment, and if you apply an electric field in addition to the magnetic field, the electric field will exert a tiny additional torque on the neutron. That torque will change the precession rate. If the electric field points in the same direction as the magnetic field, the precession speeds up slightly. If the electric field points in the opposite direction, the precession slows down. By flipping the direction of the electric field and measuring how the precession rate changes, you can extract the size of the neutron's electric dipole moment. The change in precession rate is proportional to the dipole moment. Measure the change precisely enough, and you can set an upper limit on how large the dipole moment can be. The problem is that the expected change is absurdly small. For a dipole moment at the current upper limit, the change in precession rate is less than 1 part in 10 to the 8th. You are measuring a signal that is buried under noise by 8 orders of magnitude. Everything has to be perfect. The magnetic field has to be stable to better than 1 part in 10 to the 10th. The electric field has to be uniform and well calibrated. The temperature has to be controlled so that stray thermal fluctuations do not mimic a signal. The walls of the neutron storage bottle have to be clean and smooth so that neutrons do not depolarize when they bounce off the walls. A single stray magnetic field from a piece of equipment in the next room can ruin the measurement. The experiments take years to run and require the most sensitive magnetometers ever built. One of the key challenges is dealing with systematic errors. A systematic error is anything that causes a fake signal, something that looks like an electric dipole moment but is actually caused by something else. Magnetic field gradients, for instance. If the magnetic field is not perfectly uniform, it can create a false signal that mimics an electric dipole moment. Experimentalists spend enormous amounts of time mapping the magnetic field inside their apparatus, measuring it at hundreds of points, modeling how the neutrons move through the field, and correcting for any imperfections. Another source of systematic error is something called the geometric phase effect, where the neutron spins pick up an extra phase shift just from moving through a curved or rotating magnetic field. That phase shift has nothing to do with an electric dipole moment, but it can look like one if you are not careful. Decades of work have gone into identifying and eliminating these systematic effects. The current generation of neutron electric dipole moment experiments is pushing the limits of what is possible. The experiment at the Paul Scherrer Institute, which set the current upper limit, used a double-chamber design where two separate volumes of ultra-cold neutrons were stored simultaneously in opposite magnetic fields. Any real electric dipole moment signal would show up with opposite signs in the two chambers, while most systematic errors would show up with the same sign. By comparing the signals from the two chambers, the experimentalists could cancel out most of the systematics and isolate the true dipole moment signal if one existed. The result, after 16 years of data collection and analysis, was consistent with zero. No dipole moment detected. Upper limit, 1.8 times 10 to the negative 26 electron centimeters. That null result rules out some theories. Certain versions of supersymmetry predicted dipole moments larger than that limit, and those versions are now excluded. Other theories are still allowed. The experimental limit is not tight enough yet to rule out all possible sources of new CP violation. So the search continues. A new experiment, called N2-EDM, is under construction at the Paul Scherrer Institute. It will use a larger storage volume, better magnetic field control, and more ultra-cold neutrons to push the sensitivity down by another factor of 10 or more. The goal is to reach a limit of 10 to the negative 27 electron centimeters or better by the end of the decade. Another experiment, called NADM, at Oak Ridge National Laboratory in the United States, is using a different technique involving superfluid helium to trap and measure ultra-cold neutrons. A third experiment in Japan is exploring yet another method. All of them are chasing the same target. A signal that might not be there, but that would be revolutionary if it is. The connection to cosmology makes this search unusually important. Most particle physics experiments are testing specific predictions of specific theories. This one is testing something more fundamental. If the neutron has a measurable electric dipole moment, it means CP violation is stronger than the standard model allows. And if CP violation is stronger, it opens the door to baryogenesis mechanisms that could explain the matter-antimatter asymmetry. The neutron becomes a direct link between the smallest scales of particle physics and the largest scales of cosmology. A connection between what happens inside a particle 1 femtometer wide and the structure of a universe 93 billion light-years across. There is also a more subtle point. The neutron's electric dipole moment is not just sensitive to new particles or new forces. It is sensitive to the vacuum itself. The vacuum, in quantum field theory, is not empty. It is filled with fluctuating fields, virtual particles popping in and out of existence, and constant low-level activity that affects the properties of real particles. Some theories suggest that the vacuum has a preferred direction, a kind of cosmic alignment, that could show up as an electric dipole moment in particles like the neutron. If that is true, measuring the neutron's dipole moment would be measuring a property of the vacuum, a property of space itself. The universe might not be as isotropic, as direction-free, as we assume. There could be a built-in asymmetry at the quantum level, hidden from view but detectable in precision experiments. The fact that the neutron's electric dipole moment has not been found yet does not mean the search has failed. Every null result tightens the constraints on new physics. Every improved upper limit rules out more possibilities and narrows the window where new phenomena could be hiding. The absence of a signal is itself information. It tells us that if there is new CP violation beyond the standard model, it is either very weak or very cleverly hidden in a way that does not show up in the neutron. Either way, we learn something. But the possibility remains that the next generation of experiments will find something. A small deviation from zero. A shift in the precession rate that cannot be explained by known physics. If that happens, if the neutron's electric dipole moment is measured and confirmed, The implications would be immediate and profound. It would mean the standard model is incomplete. It would mean there are new sources of CP violation waiting to be discovered. It would mean the matter-antimatter asymmetry has a new candidate explanation. And it would mean the neutron, the particle that spent the first 3 decades of the 20th century hiding in plain sight inside every atomic nucleus, has revealed yet another secret, another layer of complexity, another crack in the picture we thought we understood. The neutron has already forced us to rethink what particles are. It revealed quarks. It revealed gluons. It revealed that spin is distributed and that mass is mostly energy. And now it is sitting at the center of one of the most important questions in all of physics. Why does the universe contain matter? Why are we here? The neutron might know. And if it does, the answer is written in the tiniest possible shift in how it spins in an electric field. A shift so small that we are only just now learning how to measure it. A shift that, if it exists, would connect the neutron to the first moments of the universe and to the processes that made galaxies and stars and planets and eventually us. The search for the neutron's electric dipole moment is not just an experiment. It is a question aimed at the fabric of reality, a test of whether the universe has a handedness, a bias, a built-in asymmetry that allowed matter to win and antimatter to lose. The neutron is the messenger, and we are listening. The neutron's electric dipole moment is still out there, sitting at the edge of what we can measure, waiting to be found or confirmed absent. But whether the next generation of experiments finds a signal or pushes the upper limit down another order of magnitude, the neutron has already given us more than anyone in 1932 could have imagined. It started as a bookkeeping error, a missing piece of mass that did not add up. It became the key to understanding how atomic nuclei hold together, how stars burn, how the strong force works, and why the universe is made of matter instead of radiation. The neutron is not just a particle, it is a laboratory, a window into the fundamental forces that built everything we see. And its legacy, the things we have learned from studying it, and the things we are still learning, reaches into every corner of physics. The paradox that kicked off this entire story is still the best place to start. The neutron has zero electric charge. That is not approximate. That is exact to within the tightest experimental limits we can measure. The current bound is about -2 × 10 to the -22 electron charges, with an uncertainty of about 8 × 10 to the -22. That is 22 orders of magnitude smaller than the charge of a single electron. For all practical purposes, the neutron's charge is zero. It does not interact with electric fields. It does not leave tracks in cloud chambers. It drifts through electromagnetic environments like a ghost. And yet the neutron has a magnetic moment, a strong one, about -1.913 nuclear magnetons, pointing opposite to the neutron's spin, roughly 2/3 the magnitude of the proton's moment. That magnetic moment means the neutron behaves like a tiny bar magnet. It processes in magnetic fields. It aligns itself with or against external fields, depending on its spin state. It interacts with other magnets. It does all the things a charged particle spinning in place would do, except the neutron is not charged. The charge is zero. The magnetism is not. That contradiction, charge neutral but magnetically active, is what forced physicists to dig deeper, to abandon the idea that the neutron was a fundamental particle and accept that it had internal structure. Structure made of quarks, one up quark with charge positive 2/3, two down quarks, each with charge negative 1/3. Add them up and you get zero. No net charge. But the quarks are not sitting still. They are moving, spinning, exchanging gluons, constantly reconfiguring in a dynamic high-energy environment where nothing ever settles into a fixed position. The quarks have charge, the quarks have spin, and when charged particles with spin move around inside a confined space, they generate magnetic fields. The two down quarks, with their negative charges, dominate the magnetic moment because there are two of them, and because the distribution of their motion inside the neutron gives them more leverage. The up quark contributes a moment in the opposite direction, but it is outvoted. The result is a net magnetic moment pointing opposite the neutron's spin with a magnitude that matches the measured value almost exactly. The paradox is not a paradox anymore. It is a consequence of the neutron's internal structure, a signature of the quarks inside. That realization, that the neutron is composite, was the beginning of quantum chromodynamics. The theory that describes how quarks are bound together by gluons, how the strong force operates, how confinement works, and why you can never pull a quark out of a proton or neutron and study it in isolation. QCD is one of the three pillars of the standard model of particle physics. It sits alongside the electroweak theory, which unifies electromagnetism and the weak force, and together they describe every particle interaction we have ever observed except gravity. QCD is the hardest of the three theories to work with. The math is brutal. The force gets stronger as you pull quarks apart, which is the opposite of every other force, and that nonlinear behavior makes the equations almost impossible to solve analytically. But the theory works. It predicts the masses of hadrons, the decay rates of unstable particles, the behavior of quarks and gluons in high-energy collisions, and the properties of neutrons and protons down to fractions of a percent. Every prediction that can be tested has been tested. Every test has come back consistent. QCD is correct, and the neutron is one of the clearest places to see QCD in action. Because the neutron is not just a test case, it is a tool, a probe, a way to study the strong force and the structure of matter at the smallest scales. Neutrons are ideal for this because they are neutral. They do not interact strongly with the electromagnetic fields that dominate most experiments. They pass through electron clouds without deflecting. They do not feel the repulsive electric force that pushes protons away from atomic nuclei. A neutron can drift deep inside a material, into the spaces between atoms, into the cores of molecules, and interact directly with the nuclei and the magnetic structures there. That makes neutrons uniquely useful for studying condensed matter, the branch of physics that deals with solids, liquids, and everything in between. Neutron scattering is the technique. You take a beam of neutrons, slow them down to the right speed so their wavelength matches the atomic spacing in the material you are studying, and fire the beam at a sample. The neutrons scatter off the nuclei and the magnetic moments inside the sample. By measuring the angles and energies of the scattered neutrons, you can reconstruct the positions of the atoms, the arrangement of the spins, and the dynamics of how the atoms and spins are moving. Neutron scattering has been used to study everything from superconductors to biological molecules to the structure of proteins to the magnetic properties of materials that might one day be used in quantum computers. It is a workhorse technique, and it exists because the neutron has the right combination of properties: no charge, so it penetrates deep; a magnetic moment, so it interacts with spins; a mass comparable to atomic nuclei, so it exchanges energy efficiently; a neutral particle that can still see magnetism. That is the neutron's niche. One of the key features of neutron scattering is that it is sensitive to magnetic correlations that are perpendicular to the scattering vector. That sounds technical, but it matters. When you scatter light off a material, the light interacts with electric charges, and the scattering depends on the charge distribution. When you scatter neutrons, the neutrons interact with nuclear positions and with magnetic moments, and the magnetic scattering depends on which way the spins are pointing relative to the direction of the scattered neutron. If the spins are aligned perpendicular to the scattering direction, the scattering is strong. If the spins are parallel, the scattering is weak or absent. This directional sensitivity means neutron scattering can map out not just where the spins are, but which way they are pointing. You get a full three-dimensional picture of the magnetic structure. No other technique gives you that level of detail at atomic scales. The Institut Laue-Langevin in France is one of the world's leading facilities for neutron scattering. The institute operates a high-flux reactor that produces an intense beam of neutrons, and researchers from around the world come to use it. The IL has been running since 1972, and in that time it has contributed to thousands of studies across physics, chemistry, biology, and materials science. The neutron, a particle discovered as a solution to a mass discrepancy, has become an indispensable tool for understanding the properties of matter. Not just nuclear matter, all matter. From the structure of viruses to the behavior of quantum magnets to the arrangement of atoms in alloys, neutron scattering provides information that no other method can. The neutron also plays a central role in nuclear reactions. When a neutron collides with a heavy nucleus like uranium-235, the nucleus can absorb the neutron and become unstable. The unstable nucleus splits, releasing energy, more neutrons, and lighter fragments. This is nuclear fission, the process that powers nuclear reactors and nuclear weapons. The neutrons released in one fission event can trigger more fission events in nearby nuclei, creating a chain reaction. Control the chain reaction, and you have a reactor that generates electricity. Lose control, and you have an explosion. The neutron is the currency of nuclear fission, the particle that carries the reaction from one nucleus to the next. Without neutrons, fission would not be self-sustaining. You would need to supply energy to split each nucleus individually, and the process would not be useful for power generation. The discovery of fission in 1938, just 6 years after Chadwick discovered the neutron, transformed the world. It led directly to the Manhattan Project, to the development of nuclear weapons, to the Cold War arms race, and to the construction of hundreds of nuclear reactors that now supply about 10% of the world's electricity. The neutron sits at the center of all of it, not because the neutron is special in some mystical sense, but because the neutron has the right properties for the job. It is heavy enough to carry significant kinetic energy. It is neutral, so it is not repelled by the positively charged nucleus, and it can be absorbed by heavy nuclei without requiring a huge input of energy to overcome the electromagnetic barrier. Protons cannot do that. Electrons cannot do that. Only neutrons. In astrophysics, the neutron is even more central. When massive stars die and their cores collapse, the result is either a neutron star or a black hole. Neutron stars are exactly what the name suggests, stars made almost entirely of neutrons. The density is so extreme that the electrons and protons in the original atomic nuclei have merged into neutrons through the weak force. What you are left with is a ball of neutron matter held up against further collapse only by neutron degeneracy pressure. A neutron star is the closest thing in nature to a macroscopic atomic nucleus, a nucleus the size of a city, containing more mass than the Sun. The neutron is the structural element, the building block. Without neutrons, without the quantum mechanical pressure that keeps them from all occupying the same quantum state, the star would collapse into a black hole immediately. Neutron stars are also the sites of some of the most extreme physics in the universe. The magnetic fields of magnetars, the bursts of gamma rays from starquakes, the emission of gravitational waves from binary neutron-star mergers, the production of heavy elements in neutron-star collisions, all of it depends on the properties of neutrons at densities far beyond anything we can reproduce in a laboratory. When two neutron stars spiral into each other and merge, as happened in the event detected in 2017, the collision ejects a cloud of neutron-rich material that undergoes rapid neutron capture. Neutrons are absorbed by atomic nuclei faster than the nuclei can decay, building up heavier and heavier elements. Gold, platinum, uranium, all the elements heavier than iron that cannot be produced by normal stellar fusion, are forged in neutron star mergers. The neutron is not just a particle, it is the raw material for half the periodic table. The neutron is also unstable when it is free. A neutron outside a nucleus decays after about 10 minutes, splitting into a proton, an electron, and an antineutrino. The decay is mediated by the weak force. One of the down quarks inside the neutron transforms into an up quark, emitting a W boson that immediately decays into an electron and an antineutrino. The neutron becomes a proton. The process is called beta decay, and it is one of the primary ways the weak force manifests in everyday matter. Inside a stable nucleus, neutrons do not decay because the energy balance is different. The strong force holding the nucleus together provides enough binding energy to make the neutron stable, or at least long-lived. But free neutrons, the kind you get from a reactor or a spallation source, have a finite lifetime. That lifetime has been measured with extraordinary precision, and the current accepted value is about 880 seconds, 14 minutes and 40 seconds. Not long, but long enough to do experiments, except there is a problem. Two different methods for measuring the neutron lifetime give two different answers. One method, called the beam method, counts how many neutrons decay as they travel down a beamline. The other method, called the bottle method, traps neutrons in a magnetic or material bottle and counts how many are left after a certain amount of time. The beam method gives a lifetime of about 888 seconds. The bottle method gives about 879 seconds. The difference is about 9 seconds, and the uncertainty on each measurement is only about a second. The two results do not overlap. They disagree by more than 4 standard deviations. That is not supposed to happen. Either one of the methods has a systematic error that nobody has identified yet, or something strange is going on. One proposed explanation is that some of the neutrons in the bottle method are decaying into something other than a proton, electron, and antineutrino. A dark matter particle, perhaps, a particle that does not interact with the detectors and therefore goes unnoticed. If a small fraction of neutrons decay into dark matter, the bottle would lose neutrons faster than expected, and the measured lifetime would be shorter. That would explain the discrepancy. It would also be a sign of physics beyond the standard model. The neutron lifetime anomaly is not the only hint that the neutron might be hiding something. The search for the neutron's electric dipole moment, the subject of the previous chapter, is ongoing. The absence of a detected dipole moment so far has ruled out some theories, but it has not closed the door. There is still room for new physics to show up in the neutron's properties, new sources of CP violation, new particles that interact with quarks in ways the standard model does not predict, new forces that couple to neutrons but not to protons or electrons. The neutron is a composite particle, which means it is sensitive to anything that affects quarks or gluons. And because it is neutral, it does not have the complications that come with electromagnetic interactions. It is a cleaner probe, a quieter place to look for signals that would be drowned out in a charged particle. One of the future frontiers is ultra-cold neutron physics. Ultra-cold neutrons are neutrons that have been slowed down to the point where they can be trapped in bottles made of ordinary materials. At those speeds, the neutron's kinetic energy is so low that they reflect off the walls of the bottle rather than being absorbed or passing through. You can store ultra-cold neutrons for hundreds of seconds, long enough to perform extremely precise measurements. The electric dipole moment experiments use ultra-cold neutrons, so do experiments measuring the neutron lifetime. So do experiments testing fundamental symmetries like CPT symmetry, which combines charge conjugation, parity, and time reversal. Any deviation from CPT symmetry would be a violation of one of the most fundamental principles in physics, and it would point directly to new physics. The neutron is one of the best places to test CPT because the measurements can be so precise. Another frontier is neutron interferometry. An interferometer is a device that splits a beam of particles into two paths, lets the paths travel through different environments, and then recombines them. If the particles picked up a phase shift during their travel, the two paths will interfere when they recombine, and you can measure the phase shift by looking at the interference pattern. Neutron interferometers have been used to test quantum mechanics, to measure the effects of gravity on quantum particles, and to study how neutrons interact with magnetic fields and materials. The fact that you can do interferometry with neutrons, with particles that weigh almost 2,000 times as much as an electron, is remarkable. It shows that quantum mechanics applies to massive particles just as much as it does to light. The neutron, despite being a composite particle made of quarks and gluons, still behaves as a single quantum object. Its wave function can be split and recombined. Its phase can be controlled. It is a quantum particle in every sense, and that makes it useful for testing the limits of quantum mechanics. Neutrons are also being used to search for new forces. If there is a fifth force, something beyond gravity, electromagnetism, the weak force, and the strong force, it might show up as a tiny anomalous interaction between neutrons and other particles. Several experiments have looked for deviations from the inverse square law of gravity at short distances, using neutrons as test particles. So far, no deviations have been found, but the searches continue. The sensitivity improves every year. If a new force exists and couples to neutrons, we will find it eventually. The neutron is patient. It has been hiding secrets for 90 years. It can wait a little longer. The broader point is that the neutron has become a platform, a system that is well understood in some ways and still mysterious in others. A particle where the standard model makes precise predictions, and where any deviation from those predictions would be a clear signal of something new. The neutron is not exotic. It is common. It is stable inside nuclei. It is produced in huge numbers by reactors and spallation sources. It is easy to work with, at least compared to particles that live for a millionth of a second and require billion-dollar accelerators to produce. The neutron is accessible, and that accessibility makes it one of the best tools we have for probing the frontier of physics. There is also a philosophical point worth making. The neutron was discovered because the numbers did not add up. Atomic masses were too large. The periodic table did not make sense. Something was missing. Chadwick found it, and the discovery resolved the immediate problem. But it opened a deeper question. What is the neutron made of? That question took 30 years to answer, and the answer was quarks. But finding quarks opened another question. How are quarks bound together? That question led to quantum chromodynamics, and QCD opened more questions. Where does the neutron's spin come from? Why does the neutron have a magnetic moment? What is the neutron's electric dipole moment? Each answer leads to another question. That is how science works. You solve one problem and uncover two more. The neutron is not a solved problem. It is an ongoing investigation, a particle that keeps giving us new puzzles to work on. The legacy of the neutron is not just the discoveries it enabled, it is the way it changed how we think about particles. Before the neutron, particles were simple. Electrons were points of charge, protons were points of positive charge. The neutron was supposed to be a neutral partner to the proton, nothing more. Instead, it turned out to be a window into a hidden world of quarks and gluons and forces that operate at scales smaller than we can see directly. The neutron taught us that particles are not fundamental just because they are stable, that neutrality does not mean absence, that magnetism can exist without net charge, that structure matters, that the universe at small scales is more complicated, more dynamic, and more interesting than anyone in the early 20th century could have imagined. And the neutron is still teaching us. Every new experiment, every tighter limit on the electric dipole moment, every refined measurement of the lifetime, every neutron scattering study of a new material adds to the picture. The neutron is a laboratory in a box, a bound state of the strong force that we can hold in our hands, or at least in magnetic bottles, and interrogate with the best tools we have. It is a bridge between nuclear physics and particle physics, and condensed matter physics, and astrophysics and cosmology. It connects the smallest scales to the largest. The structure of a neutron, 1 femtometer wide, determines the properties of neutron stars, 20 kilometers wide. The magnetic moment of a single neutron, measured in nuclear magnetons, scales up to the magnetic fields of magnetars, the strongest fields in the universe. The neutron's decay, mediated by the weak force, is the same process that drove nuclear synthesis in the early universe and that powers the sun. The neutron is everywhere. It is in every atom, heavier than hydrogen. It is in your bones, your blood, your brain, and it is in every star, every planet, every galaxy. The neutron is not exotic, it is fundamental, not in the sense of being indivisible, but in the sense of being essential. A building block of everything we see. The paradox that started this story, the neutron's magnetic moment, despite its lack of charge, is no longer a paradox. It is a solved problem, a consequence of the Quark model and quantum chromodynamics. But the solution did not close the book on the neutron. It opened a new chapter. Because once you understand that the neutron is composite, you realize that every property of the neutron is a window into the dynamics of the strong force. The magnetic moment tells you about the quark distribution. The spin tells you about the contributions from quarks, gluons, and orbital motion. The mass tells you about the energy stored in the gluon field. The lifetime tells you about the weak force. The electric dipole moment, if it exists, will tell you about CP violation and maybe about why the universe is made of matter. Every measurement of the neutron is a measurement of the forces that built the universe. The neutron's legacy is that it refuses to be simple. Every time physicists thought they understood it, it revealed another layer, another complication, another opportunity to dig deeper. The neutron is not a finished story. It is an ongoing experiment, a particle that has been studied for 90 years and is still full of surprises. The neutron is a reminder that the universe does not owe us simplicity, that the rules at small scales are not the rules we see in everyday life, that particles are not little billiard balls. They are quantum mechanical objects made of smaller pieces held together by forces that do not behave the way forces at human scales behave. The neutron is a door, and every time we walk through it, we find something we did not expect. The future of neutron physics is bright. New experiments are being built, new techniques are being developed. The electron-ion collider, scheduled to come online in the early 2030s, will probe the internal structure of protons and neutrons with unprecedented precision. New neutron sources, both reactors and spallation sources, will produce more intense beams for scattering experiments. New ultra-cold neutron experiments will push the sensitivity to the electric dipole moment down by another order of magnitude. New theoretical tools, lattice QCD simulations on ever-faster supercomputers, will calculate the properties of the neutron from first principles with ever tighter error bars. Every advance brings us closer to a complete understanding, or at least to the next set of questions. The neutron has been lying to us for 90 years, not through deception, but through the sheer impossibility of its properties. A particle with no charge that behaves like a magnet. A particle that should be simple but is made of quarks and gluons in constant motion. A particle that is stable inside a nucleus but decays in minutes when free. A particle that is everywhere, essential and still not fully understood. The neutron is a paradox wrapped in a mystery inside a nucleus. And unraveling that mystery has been one of the great achievements of 20th and 21st century physics. The journey is not over. The neutron still has secrets. And as long as there are physicists with the patience